तुम्ही बसला नाही तर हो तुम्ही पुढे मी आहे तिकडे जिथं लागेल तिकडे
हॅलो
इथंच आहे याच
हॅलो
मी
सर माझा आवाज येतोय? Am I clear and loud? Yes. Thank you. Good morning, sir.
Yes. Hello, madam.
Yeah, sir. Good morning, sir.
Morning. I think Dr. Dubal have.
Yeah, he's there. He's there, sir. He's joined.
Yeah. Confirm whether other resource person has joined or not.
Yes, sir. Sir, our resource person is there. So, shall we start?
Yeah. Madam, proceed.
Okay, sir. Good afternoon, one and all. I welcome you all to the International E-Conference on Advancements in Material Science, Trends and Application, organized by Department of Physics in collaboration with IQAC. I am Dr. Leena Mishram. It's my pleasure to be your host for the day. Before we delve into the fascinating world of material science, let me take a few moments to welcome our esteemed guests and speakers from around the globe who will be sharing their insights on advancement in material science and applications. On behalf of Mahatma Phule Arts and Commerce College, Panvel, I take the opportunity to welcome today's keynote speaker, Professor Deepak Dubbal from School of Chemistry and Physics, Queensland University of Technology, Brisbane, Australia. It's my honor to welcome today's resource person, Dr. Rahul Salunke, Associate Professor, Department of Physics, Indian Institute of Technology, Jammu, India. It's my privilege to welcome another resource person, Professor Rupesh Devan, Department of Metallurgy, Engineering and Material Science, Indian Institute of Technology, Indore. I also welcome Honorable Principal Dr. Ganesh Thakur Sir, Vice Principal R.A. Patel, Dr. N.B. Pawar, Mr. Sanjay Gaikwad, Organizing Secretary and Head of Physics Department. I welcome Dr. Girish Gund, Convener of today's conference, Mr. Sopan Gove, IQAC Coordinator. We are extremely delighted to have more than 550 participants joining us from all over the world as we have gathered on this virtual platform. I extend a warm welcome to all the researchers, academicians, faculty members, student participants who are joining us through YouTube channel as the YouTube link has been shared in the group and also on Google Meet. The sole purpose of this international conference is to provide a platform for experts to share their insights, research findings, and experiences regarding the advancement in material science, as it is driving a technological revolution with far-reaching implications from nanomaterial to smart materials. The breakthrough are not only transforming industries, but also addressing global challenges such as renewable energy and environmental sustainability. It has not only transformed industries, but also laid foundation for innovations, shaping the future of technology and improving our daily lives. As we witness the ongoing revolution in material science, it is clear that the future holds even more possibilities. So let's begin with the welcome address by Honorable Principal Dr. Ganesh Thakur Sir. Sir is being a guiding force behind the academic excellence of our institute. Under his visionary leadership, our institute has achieved remarkable milestones. The college has been re-accredited with A+ grade in the 4th cycle of NAC, and also the college has received a grant under DBT Star Scheme, DBT Star College Scheme. Sir has also worked as an ex-secretary of Rayat Shikshan Samstha, which is the largest educational institute in Asia. Sir has earned multiple prestigious awards throughout his career, including the Best Principal Award by University of Mumbai. So without further ado, I request Honorable Principal Dr. Ganesh Thakur Sir to deliver a welcome address.
Thank you, Madam. At the outset, I pay my tribute to great social reformer and visionary educationist Mahatma Jyotiba Phule and Karmavir Bhaurao Patil for their selfless service to the masses. Dignitaries present online for this international e-conference, keynote speaker, Professor Dr. Deepak Dubbal, School of Chemistry and Physics, Queensland University of Technology, Brisbane, Australia. Resource person, Dr. Rahul Salunke, Department of Physics, Indian Institute of Technology, Jammu, India. Professor Rupesh Devan, Department of Metallurgical Engineering and Material Science, Indian Institute of Technology, Indore, India. Mr. Bhavesh Sinha, University of Mumbai. Dr. Archana Kalekar, ICT Mumbai. Dr. Abhijit Kadam, Wilson College, Mumbai. Dr. Deepak Gaikwad, KMC College, Khopoli. Directors and principals of various institutes, vice principals of college, Dr. Rajaram Patil and Mr. Namdev Pawar, IQAC coordinator, Mr. Sopan Gove, convener of the workshop of this e-conference, Dr. Girish Gund, organizing secretary and head department of physics, Mr. S.L. Gaikwad, research scholars, faculty members, and dear students. It is my extreme pleasure to welcome you all for the International E-Conference organized by Department of Physics in collaboration with IQAC on the theme Advancements in Material Science, Trends and Applications. Friends, our college is run by Rayat Shikshan Samstha which is one of the largest educational institutes in Asia. Education through self-help is motto of our Samstha, and it strives to uplift the educational standard of deprived and downtrodden section of the society. State government as well as central government has honored our Samstha with Ideal Educational Institute Award for its praiseworthy contribution in the field of education. Our college was established in 1970 and has completed 53 glorious years with a vision to provide quality education to all classes of the society. Our outstanding achievements in the recent past includes A+ grade in 4 cycle of NAC accreditation, Best College Award by University of Mumbai, Karmavir Puraskar from our parent institution, ISO certification from International Accreditation Forum, and DBT Star College Grant from Government of India. We all are marching ahead with the mission to achieve some short-term and long-term goals as per our perspective plan. Our college promotes research activities through Center of Innovation, and Incubation, institutional minor research projects, research inspirational awards, best performer awards, and organizing online as well as offline conferences. Faculty members of our college have published 24 patents in last 3 years, out of which 11 patents are granted, and some design patents are filed by faculties which will be published soon. Today's e-conference is organized by Department of Physics. It offers UG and PG research programs to the aspiring students. The department has developed 2 research labs for the research scholars under DST Serve Major Research Project. Dr. Girish Gund of the department has published 4 Korean patents which are granted. I feel proud to mention that the participants in large numbers attend each and every conference organized by our institute. The participants from 25 states of India, as well as the participants from South Korea, Nigeria, Saudi Arabia, and South Africa are present online for this conference. I am happy to inform you that we have received more than 75 abstracts for this conference from research scholars. Material science research is a multidisciplinary field that focuses on understanding the properties and behavior of different materials at the atomic and molecular level. Over the years, significant advancement in material science have led to revolutionary breakthroughs across various industries, including electronics, energy, healthcare, transportation, and more. Material science research plays a vital role in the development of new materials and the enhancement of existing ones, with significant implications for numerous industries and technologies. It encompasses a wide range of materials such as metals, polymers, ceramics, composites, and semiconductors, and it investigates their composition, structure, properties, and synthesis methods. These advancements have resulted in the discovery of novel materials with exceptional properties, paving the way for revolutionary applications in the areas such as electronics, energy storage, healthcare, transportation, and environmental sustainability. One of the most exciting areas of material science research lies in the field of nanomaterials. Nanomaterials are engineered materials with unique properties at the nanoscale level, allowing for enhanced performance in numerous applications. Researchers have made remarkable progress in synthesizing nanomaterials with tailored properties such as high strength, exceptional electrical conductivity, and increased catalytic activity. Electrical conductivity, these advancements have opened up the possibilities for developing more efficient energy storage devices, highly sensitive sensors, and improved drug delivery systems. The quest for sustainable energy sources has been a driving force behind material science research. Innovations in this field have led to the development of new materials for more efficient solar cells, energy storage devices, and fuel cells. For instance, perovskite solar cells have gained significant attention due to their high efficiency and low cost of fabrication. Material science research plays a crucial role in addressing environmental challenges. Scientists are developing innovative materials for pollution control, water purification, and waste management. For example, nanomaterials with photocatalytic properties can efficiently degrade organic pollutants in water and air. Researchers are designing novel materials that are biocompatible, bioactive, and can integrate with the human body seamlessly. These materials are used in tissue engineering, regenerative medicine, and implantable medical devices. Bioactive ceramics, biodegradable polymers, and tissue scaffolds are some of the innovative biomaterials that have revolutionized medical treatments, enabling faster healing, reduced rejection rates, and improved patient recovery. Scientists are investigating alternative materials and manufacturing techniques that minimize the waste, reduce energy consumption, and lower carbon emission. For example, additive manufacturing, commonly known as 3D printing, allows for precise fabrication of complex structures, reducing material waste compared to traditional manufacturing methods. Moreover, researchers are exploring bio-based materials derived from renewable resources as alternatives to conventional plastics, reducing reliance on fossil fuels. Material science research continues to push the boundaries of innovation, offering remarkable opportunities for a sustainable future. Advancements in nanomaterials, energy solutions, smart materials, environmental remediation, biomedical engineering, and sustainable manufacturing have the potential to revolutionize various industries. I am confident that the resource person will enrich us with their expertise on the theme of the conference. Before I conclude, once again, I welcome you all for this international e-conference. Thank you very much.
Thank you, sir. Thank you for such a warm welcome. And your words have really set a tone of inspiration and purpose for this conference. Thank you once again, sir. Now I request Mr. Sopan Gove, IQAC coordinator, to introduce our keynote speaker.
Thank you, madam. Good afternoon to one and all present for International Conference on Advancements in Material Science. I am privileged to introduce the keynote speaker of this e-conference, Professor Dr. Deepak Dubal. Dr. Dubal is presently working as professor at the Queensland University of Technology, Australia. Sir is well known for his outstanding contribution to the field of clean energy conservation and storage system such as supercapacitors, batteries, and bioelectric nano generators. His impressive career and numerous accolades reflect his dedication to advancing knowledge and fostering sustainability. Professor Dubal has earned multiple prestigious fellowships throughout his career, including the Brain Korea 21 Fellowship at Gwangju Institute of Science and Technology in South Korea in 2011, the Alexander von Humboldt Fellowship at Chemnitz University of Technology, Germany in 2012, the Marie Curie Fellowship of the Catalan Institute of Nanoscience and Nanotechnology, Spain in 2014, and recently, Sir has been honored with the Vice Chancellor Fellowship at the University of Adelaide in Australia. In 2018, he was awarded an exceptionally competitive ARC Future Fellowship, which marked a significant milestone in Sir's career and led him to his transition to Queensland University of Technology, Australia. Dr. Dubal's research has resulted in a prolific publications records with over 300 peer-reviewed journal articles, which has attracted over 20,000 citations. His H index is 76 and I-10 index is more than 200. Sir has received international recognition for his contributions, including being listed among the world's top 2% of scientists by Stanford University and top 100 material scientists in Australia as well. Dr. Dubal's experience has led to global engagements, including appointments as a visiting guest professor at Mid Sweden University, Sweden, and Indian Institute of Technology, Madras, India. He has also received recognition as a foreign young associate fellow of the Maharashtra Academy of Science, India. Dr. Dubal's team is extending their research into the areas such as radiant heaters, biomass valorization, and battery recycling, aligning with the principles of circular economy, sustainable practices. He also serves as an editor of Nature Scientific Reports, associate editor of Battery Energy and Batteries and Supercaps, published by Willy Publications. Thank you, sir, being with us as a keynote speaker. With all this short introduction, I request Dr. Dubal to deliver keynote address. Over to you, sir.
Okay, thank you very much for a nice introduction. And it is always been my privilege, and I always overwhelmed to, interact and deliver a talk in the conferences, which happens to be in India. And what I will do is I will start sharing my screen. I hope you can hear me properly.
Yes, sir, you are audible.
Yeah, so can you see my screen now?
Yes, sir.
Yes.
Okay, that's great. Thank you. Okay, thank you very much again. So it is already end of the day here in Australia. So it's 5 o'clock in the evening. And yeah, I will try to keep my lecture as simple as possible, and I will try to explain it in the simple words that I can imagine that most of the audience is students from college and different universities. So I will try to keep my lecture as simple as possible. So I would again like to thank all of you, and I would like to thank organizers and Dr. Girish Kun for inviting me to deliver a lecture. And I also would like to thank our principal of the college and the other members who has contributed in organizing such beautiful conference. So I would like to talk today about the low carbon emission technologies which we are using in manufacturing of materials. So I just intentionally put this picture into the background, which you can see that it's some kind of a chimney, and it's throwing a lot of fog outside, like it's kind of a smoke. So this is basically what we consider that as a carbon emissions, but that is not the case. And I will also talk a little bit about, we always talk about this new green and clean energy technologies. For example, the solar cells, hydrogen is coming, and even the batteries, and we call that all technologies as a clean energy technologies. But we really need to ask a question to ourselves whether all these technologies are really clean, and what does exactly mean by clean or sustainable technologies, or like a clean and green technologies. So before starting with the lecture, I always like to introduce myself through my university. So this is, as you can see, this is the Australian map, and you can see that we have 6 different states. So yeah, we are not really very happy with Australia for now because they recently won the World Cup. But yeah, so it's a game. So basically, as you can see, like we have 6 different states, and here is the Queensland. So this is one of the state, and you can see here a small red dot, which is a Brisbane, which is again a small city in Queensland, and this is the place where my university is. So basically, this is the beautiful campus of the Queensland University of Technology, and we have 2 different campuses. This is one of the main campus which we have, and sometimes it is confusing to memorize the university, our university, basically, because what happens is like we have 3 to 4 different universities with the name Queensland. So for instance, we have University of Queensland, we have University of Southern Queensland, we have Central Queensland University, and our own is the Queensland University of Technology. So it's sometimes confusing to memorize, but yes, this is the technological university. And one of the very interesting thing which I always like to talk about this university is this is very young university. We started in 1989, so this is only 30 years old university, and still we are very much into at very good number at QS ranking. This campus also looks even beautiful in the night. So you can see this is what the image we got during the rainy season. So this is basically the campus of QUT. We do have internal centers. So we have a center for material science and center for clean energy, center for environment, center for agriculture, bioeconomy. So you are welcome to visit the website of the university, and feel free to ask me a question if you really want to know more about this university. And as I said, this is the very young university, just 30 years old university, but it's one of the topmost among youngest universities. And in addition to that, we are at 187th place in the QS ranking. So this is really very fastest growing university. So yeah, let's talk about like carbon dioxide emissions, as we always, and there are a lot happening around. A lot of people, they talk about carbon dioxide emissions, then climate change, and then green technologies. But what we really need to understand, what does that mean by what does the meaning of carbon dioxide emissions first? The second is like, what are the possible sources from where these carbon dioxide emissions are coming? So let's consider that we are talking about the CO2 emissions, and just to understand, what I did is like I just distributed that the carbon dioxide emissions into 3 different categories. So imagine that we are manufacturing something. So for example, mobiles, laptops, and even anything which we manufacture. So that is the one sector. So all these factories, facilities, boilers, furnaces, vehicles, all that manufacturing processes, they are the major contributor of the carbon dioxide emission. The second contributors are the uses. So whatever we are using, for example, electricity use and all that facilities. And for example, now we are talking, you all are attending this lecture and you are using the electricity, you are using the internet, and you are using so many different types of facilities. So you are already contributing a lot of different carbon dioxide emissions to the environment. So when we talk about the carbon dioxide emissions, it doesn't mean that only a smoke or only something which is coming through a burning of something. Okay, and the last and most important source of carbon dioxide emissions is the disposal. Yeah, we never care about the disposal. We buy something, we use it, and we simply throw it out. But we really need to understand, when we dispose something, that disposing is also going to contribute something to the carbon dioxide emissions. What I'm going to talk today is more about the batteries. So what are the carbon dioxide emissions involved in battery manufacturing? Because nobody wants to talk about these particular technologies. What happens is, like, whenever we talk, we always say, okay, so this is okay. Just give me a minute. Sorry. Don't come. After some time, let me finish my lecture. Thanks. Okay, yeah, sorry about that. So what I'm going to talk today is about the carbon dioxide emissions which are generating from the battery technologies. So whenever we talk about this battery or solar cell or hydrogen technologies, what we do is we simply compare these technologies with the petrol and diesel or some other gasoline type of sources. So what we need to understand is these technologies are really clean or green, or is just we are talking a lot about this carbon dioxide emissions. So whenever we do a comparison, we connect everything to the petrol and diesel, but that is not actually the case. So what is happening now is these battery technologies are moving so fast. So initially we have been using the lithium-ion batteries only into the mobiles, but now we started to use the lithium-ion battery technology in a different type of drones and electric vehicles, and then also we are using these technologies to store the solar energy or electricity which is generated through the solar power plant. So the technologies are booming so fast. So initially we were using these all technologies just for some kind of watt scale, and then kilowatt scale, and gigawatt scale, megawatt scale, and then gigawatt scale. So it is actually growing so fast. So what we do is we are now in next 5 to 10 years, we are hoping to have that all clean and green technologies. So all these lithium-ion batteries is going to dominate the market. So, and that is the main reason we really need to understand whether these technologies are really clean. So let me give you some examples. So just for the people who are not really very much aware of the lithium-ion batteries. So these are the basic components of the lithium-ion batteries. What you can see here is we have a anode material, which is basically a graphite. Then we have a cathode materials, which is a lithium intercalated cobalt oxide. And there are some other packaging and current collectors and separators and electrolytes. So these are some different bits and pieces. So the major, an important component into the lithium-ion batteries is the cathode materials. And the cathode materials cost the 50% of the battery. So for example, if you go into the market and if you are buying the electric vehicle, or if you buy a mobile into the market, which cost you, for example, $1,000. So $500 we are already paying for the battery. And from that $500, like $250 we are paying only for the cathode materials. So what we can see here is the cathode material is the most expensive part of the lithium-ion battery. So these are the different battery chemistries which are already commercialized. So you can see the LCO, LMO, LFP, NCA, NCA. So all these are different types of cathode materials. So L stands for lithium, C is for cobalt, O is for oxygen, same like M is for manganese, F is for iron, and NCA is for nickel, cobalt, aluminum batteries. So these are the famous battery chemistries. And then the bottom row where you can see the NMC, which is a nickel, manganese, cobalt chemistry, NMC. So these numbers 111442, this is just the composition of this nickel, manganese, and cobalt into different types of batteries. So this bottom row is basically the batteries which are Tesla is currently using into their electric vehicles. So what are the major sources of carbon dioxide emissions into the battery manufacturing? You can see here, what I did is I have collected several different battery chemistries. So you can see the China is manufacturing this type of battery chemistries like LFP graphite, NCA graphite. So LFP is lithium iron phosphate and graphite. So most of the things you can see the anode material is constant, which is a graphite, and cathode material is some metal oxides. And all of these are different. So these are the batteries manufactured in United States, and these are the batteries manufactured in European Union. So in Europe. So you can see here, so what happened is like all these different components of the lithium-ion battery manufacturing, it contributes a huge amount of carbon dioxide into the environment. So you can see the cathode manufacturing. So cathodes are actually contributing the huge amount of carbon dioxide. And that is why we need to understand from where exactly this carbon dioxide is coming. So you can see, you might have already seen that there are a lot of researchers, or even there are a lot of companies who are claiming that hydrogen is clean, then electric vehicles are clean. But you can see here, for example, if we want to make an hydrogen car with the capacity of 80 kilowatt fuel cell system, it needs 2 storage tanks, and it still contributes 5 tons of carbon dioxide emissions. You can also see the battery electric vehicle. It also contributes 4.2 tons of CO2 emissions. It means, like, although we are talking about these particular technologies, these technologies are also contributing a huge amount of carbon dioxide. And the reason is because all that processes or materials or whatever manufacturing processes we have been using, they are really very energy intensive, and at the same time it contributes a large amount of carbon dioxide. So you can see here, so what I did here is, if we want to manufacture a one electric vehicle, so for example a 60 kilowatts hour electric vehicle with the power electric vehicle, if we want to make it, it needs almost 207 kilos of minerals per vehicle. So you can imagine, like, we are contributing. So what does this mean is, like, the mining industry is the biggest source of carbon dioxide emissions, because we mine all these minerals. So starting from lithium, cobalt, manganese, nickel, copper, and graphite, all these minerals we contribute, we mine, and this mining is really very much energy intensive. At the same time, it contributes a lot of carbon dioxide. So let's come back to the materials manufacturing. Okay, so mining is, we need to explore the processes to be used for the materials into the mining industries. But what I would like to talk today is about these furnaces which we are using into the lab from a very long time, and we unknowingly use of these furnaces is contributing a huge amount of CO2, and I will tell you how. So you can see here, if I want to synthesize the lithium cobalt oxide material, it needs almost 800 degrees Celsius, because most of these battery materials, they are of a particular crystal structure, mostly like a spinel structure or olivine type structure or layered crystal structure. And this type of structures only form at a very high temperature, so over 600 to 700 degrees. So if I want to synthesize any cathode material into the batteries, we have to go at a temperature over 800 degrees. And this reaction, if you can see, the reaction is so long, it's a 15 to 20 hours of reaction. If I want to synthesize any carbon material, we have to go 1000 degree to 2800 degrees, because graphite can be graphitized at 2800 degrees Celsius, and the reaction time is super long. So it means, like, unknowingly we are using these all sources to manufacture the materials, and is basically contributing the huge amount of emissions. So what we can do is, and what we did is, we need to find a new processes, and that processes needs to be cleaner, first thing, and then the second thing is that all the processes needs to be efficient and fast. And what we did in our group, we have developed a new microwave technology, which is a rapid and at the same time a less energy intensive technology, and which we are claiming as a low carbon emission manufacturing process. So the microwave, so we already know the microwave. So microwave hydrothermal and microwave solution based microwave process is already into the research. A lot of researchers, they have already explored the synthesis of different nanostructures by using the microwave. But which hasn't been explored really is solid state microwave synthesis. And here what we did is we explore the microwave method to synthesize these materials, mostly the battery materials, and into using a very less time. And that help us to reduce the reaction time a lot, like significantly reduce the reaction time, and which help us to reduce the carbon dioxide emissions. So basically how the microwave works. So you can see here what I did is, like, I tried to comparatively showing here like how these two different heating systems work. So you can see here, this is the traditional heating. So what happened is, like, in the conventional furnaces, what we do is we pass the electricity to the coil, then coil heats up, and then the coil transfers heat to the environment, and then the environment heats up, and then environment passes the energy or heat to the sample. So this is what we call as the convection process. And through the convection process, the heating rate is very, very slow, somewhere around 5 degrees per minute to 10 degrees per minute. But you can see in the microwave works totally opposite. So in case of microwave directly attacks the sample. So what happens is, like, sample absorbs the microwave and it generates their heat by itself. So it's not a convection heat. And because of that, the heating rate is almost 50 degrees per minute to 100 degrees per minute. So for imagine that if I want to reach to 800 degrees Celsius with the microwave, it takes only 8 minutes. But if I want to use the traditional heating method, it takes almost 2 to 3 hours just to reach the temperature. And you can do this simple experiment at home. So for example, if you have the microwave oven, what you can do is you can get some small amount, some water or milk in a cup and put that cup into the microwave oven and turn on the microwave for 1 minute. So after 1 minute, what you can do is you can still put your hand in the microwave oven and you can still take out that cup. It means like microwave doesn't heat up the environment, it just heat up the sample. We did the demonstration. So what we did is we tried to convert this winery waste, which is a grape mark. So we have been working with the one industry, Spark Technologies, which is based in the South Australia. And what we propose to them is we can try to convert this grape mark into a hard carbon, which can go into the sodium-ion batteries. And what the results which we got are really very surprising and very exciting. What happened is, like with the microwave, because it is a localized heating at a very less temperature, somewhere around 1100 degrees, you can see this transmission electron micrograph where you can see all these graphitic structure. So we are actually forming a very highly crystalline carbon materials, like a graphitic carbon materials at a very less temperature. So as I said, if we want to synthesize a graphite, we need at least 2800 degrees Celsius temperature. But with the microwave, with just 1100 degrees Celsius, we could develop this kind of microstructure, and the feedstock is simply a winery waste. The interesting part of this investigation is the capacity. So we received almost over 400 milliamps hour per gram of capacity, which is very, very high as compared to the capacity proposed by this company, Faradian. So Faradian is a UK-based company which is recently taken over by Reliance. So Reliance is planning to manufacture the sodium-ion batteries here. So we tried this one, and this is very interesting, and we could convert any type of agricultural waste into, or biomass into a very highly graphitic carbon materials, which can go into different battery applications. So one of my PhD student, Chinmayi, she has been trying to convert this rice husk, because rice husk is a very rich source of the silicon oxide. So our plan was to convert the silicon oxide into a silicon, and that all organic matter into the carbon. So Chinmayi tried a lot of experiments by conventional heating method, and she failed so many times. What does mean by she failed is she could able to make the material, but all the time she was getting a lot of impurities. So she was getting magnesium silicate and so many different types of impurities, which was difficult to get rid of. But at the end, we decided to try the same material or same strategy in a microwave. And that was very, very impressive, that she could form all that graphitic type of carbon materials using this organic waste. But at the same time, she converted the silicon oxide into the silicon. This is very impressive in terms of, like in general, if we try to convert the, try to reduce the silicon oxide into the silicon, we end up in amorphous silicon. But this time we got a very highly crystalline silicon, but at the same time we got a very interesting capacity. The interesting part of all these investigations is we did all these processes is in 30 minutes or 40 minutes. Most of the times, all these conventional furnaces, it takes 10 hours to 15 hours to 20 hours of reaction time. And a similar way, we also try to convert this all simple glass waste. So glass is basically a silicon oxide. So one of our a visiting student, he wanted to try this, and what he did is, like, he tried to convert the silicon, like a silicon oxide, which is a glass waste, into a highly crystalline silicon. So you can see here X-ray diffraction, where you can see the very highly crystalline silicon, and it's all the processes which we have done so far, they are single step processes, and we get a very high quality pure materials which can go into the lithium-ion batteries. So not only for anode materials, we also wanted to explore if we can use this microwave process to synthesize the cathode materials. So one of my PhD student, Rebecca, she tried to synthesize the cobalt-free cathode material. The reason a lot of industries and a lot of researchers, they are interested in manufacturing the cobalt-free cathode material is because cobalt is very expensive mineral, and that has only been available in Republic of Congo. So that's the only country who mines the cobalt. So we recently developed this very high capacity cathode material, which is without cobalt, so lithium nickel manganese oxide. And you can see here the X-ray diffraction I just put here just to show you that you can see here the conventional method 800 degrees Celsius 18 hours, and we synthesize the same material using microwave at 800 degrees Celsius only in 20 minutes. So you can see there is no any difference into the structure of the material. At the same time, we tested the material for a lithium-ion battery, and we get a specific capacity which is very, very close to the theoretical specific capacity. And we also try to explore the mechanism, because in the X-ray diffraction, we didn't see a much difference. But when we did the electrochemical testing, you can clearly see that electrochemical signature of microwave synthesized material at different times is different. You can see the conventional and then the material synthesized with microwave at 45 minutes, they have the similar signature. So this means like we need at least 45 minutes to synthesize this cobalt-free cathode material using the microwave synthesis. So we also try the electrochemical stability and rate performance. So rate performance, so this is very interesting to see, like the rate performance of the materials synthesized through microwave process is really very high. So you can see here that with respect to C rate, like applied current density, the specific capacity is still managed, while with the conventional method, the specific capacity is fading very quickly with respect to applied current density. So why this happens is our hypothesis, we are still exploring the mechanism of the microwave synthesis process, but our hypothesis is because in case of microwave, when we say the reaction, like when we apply the microwaves or when we start the furnace, so it actually brings the temperature, like a synthesis temperature, like for a crystal formation temperature very rapidly. So the sample doesn't get an extra heat. And that is the reason the material which we are getting through this microwave process is very pure, defect-free, and very less impurities. And because of that reason, that is our hypothesis. We are still trying to build in situ X-ray diffraction furnace, like a furnace which we can fit into the X-ray diffraction, so that we can see that how the material is growing with respect to temperature. But so far the results are very, very impressive. We also wanted to synthesize different types of cathode materials, not only for the lithium-ion battery chemistry, but we explore the synthesis of cathode materials for sodium and potassium batteries. And the results are very, very, very nice. Like we could synthesize any type of a battery material using the microwave in a very short time. So, and the performance is very interesting. The most highlighting part of this microwave synthesis is, you can see here the the charge-discharge curve. All these electrochemical signatures, they are very, very strong. So it means like all the components into this material, they are electrochemically active, and that is the reason in the X-ray in the charge-discharge curve, whenever at the same time in a cyclic voltammetry, we can clearly see the oxidation and reduction peaks for each of this material. So it means, and that is one of the reason our hypothesis is the material formed by using the microwave synthesis is extremely pure, less defects, and is a really very, very high quality. So these are the most, this is the most of the results which we have generated. So as we started to talk about the carbon dioxide emissions, so we wanted to explore that if we use the conventional furnace, how much carbon dioxide emissions we are contributing. And if we replace the conventional furnace with the microwave furnaces, is there anything we are contributing to the, or are we reducing the carbon dioxide emissions? So what we did is, this is something which we found on Queensland government's website, where based on the energy input to the furnace, we can definitely calculate the carbon dioxide emissions. So you can see here, we have calculated the emissions which we are generating by using the microwave process and with the conventional process. So this is the resident time, and you can see with the microwave, we are actually contributing a really, really very small amount of carbon dioxide emissions to the environment as compared to the conventional furnaces. So it means like we really need to understand the manufacturing of the materials. It's not only about, so only we are trying to solve the end problem, comparing all that with the gasoline engines, but it's not only the gasoline engines, it's manufacturing of all these materials and processes and technologies of lithium-ion batteries, as well as hydrogen, and as well as the solar cells. We have to understand that all that manufacturing processes are really clean, and are we reducing the carbon dioxide emissions? So all this research is not at all at the lab scale. We have recently received an Australian Economic Accelerator grant from Australian government. We got almost $500,000. So now whatever I showed you today about the microwave synthesis of hard carbon, microwave synthesis of cathode materials. So in the past we were doing into the batch process, but we recently got a funding to purchase this big microwave pilot scale microwave furnace where we can synthesize the material in kilos. In addition to that, this furnace is not a batch process, it's a continuous furnace. So from one end, you can simply keep putting the material in, and at the end, you can just collect the product. So, and the capacity of this furnace is 5 kilos per hour. So this furnace can produce 5 kilos per hour of the material. So you can imagine if we run for 8 hours, then we can generate almost 40 kilos of material per day. And we recently received funds for this battery, and this is one of the very big project we received. We also filed a patent on this. We have submitted the IP disclosures, and we are also collaborating with the industry partners to actually commercialize this particular microwave process to manufacture the battery materials. So yeah, in addition to this particular research topic, in my research group, we also work on the supercapacitors and different types of metal ion batteries, biomass, like where we try to convert the different agricultural waste. Radiant heater, I will tell you a little more about the radiant heaters. It's one of my favorite research topic recently, and nano generators and battery recycling. So just a quick about the battery technologies which we are doing at QUT is we try to understand the mechanism. So this is one of the example I always give is about the thermal runaway or the battery failure. So you might have heard that incident happened last a few years back where we were talking about the explosion of the Samsung Note. And all the times what we did is like we started to criticize the manufacturer. So we started to criticize the Samsung. Okay, you didn't manufacture the battery properly, and that's why it exploded. But that wasn't the case. So what happened in the batteries? You can see here we have the carbon as an anode material. We have lithium intercalated metal oxide as a cathode material. So when we charge it, what happens is this lithium, these yellow balls, they move and they goes into this carbon material. But the problem is the intercalation potential, which means this potential, and then the deposition potential of lithium onto the graphite, it's very close. So both these potential are really very close to each other. So what happens is like imagine you have, and the mobile battery is discharged 80%. So now your mobile is only about 20% charged, and you will see that red light in your mobile. So that red light is nothing but a warning to you that you need to recharge the mobile, or you should not discharge mobile up to 0. So what happens is like when you discharge mobile up to 0, this lithium, instead of intercalating into the structure, it starts to deposit on the graphite. And what happens is it deposits in the form of dendrites or spike. This spike we call as dendrites, and it breaks the separator and it goes to the cathode materials. So imagine that you have two wires with the electric current. If you touch that 2 wires, what will happen? You will see the spark. So that is what happened into the batteries. Anode and cathode, both of them are at a different working potentials different working potentials. So when they comes together, it's short circuit, and it actually do the spark inside the battery. And in the battery, we use the carbonated electrolytes, which are extremely flammable, and that's why the battery explodes. So what we are doing at QUT is we are trying to do an in situ transmission electron microscopy. So we recently got this super transmission electron machine where we do a lot of in situ characterization. So what we did is we modified the TM holder. So you can see what we do is normally here, you can see the schematic. So we have this gold current collector, we apply the sample here, and we have the tungsten here, we apply the lithium, and we put this everything into the TM machine, and then through the potential stat, we apply voltage. And then we see how the material works. So you can see here on this, we recently did this analysis. So you can see this is our material. This is the material. So when actually we just start to charge the material like lithiation process, it starts to expand. And when we start to discharge, this actually starts to contract. And this is what we are actually seeing into the transmission electron microscopy. So this in situ TM actually help us to understand the materials at the atomic scale so that we can better synthesize the materials which are extremely reversible, so the lithiation and delithiation. So that is one of the very important aspect we are exploring at QUT. And the second important project which I just mentioned about the radiant heaters. So what is mean by radiant heaters is, you imagine that we have countries where the temperature goes below zero. So it's a minus temperature. So what happens is, like in the cars, we use some kind of heating system so that we can keep the car warm inside. So with the gasoline engines, what happens is, like all these petrol and diesel vehicles, what we do is that engine heats up by itself. So we take a heat from engine in the car to warm the car. But imagine in the next 5 to 10 years, we are moving from petrol diesel cars with the electric motors, like electric vehicles. So in the electric vehicles, we don't have a gasoline engine, so we have electric motors, and that electric doesn't heat up as much as the gasoline engine heats up. So we need to find a solution. Otherwise, what will happen is all these heating systems, they will drain all the energy from the batteries. So basically, what happens is, like during the winter season, the heaters, they drain almost 40% of electric power from the batteries. It means like the mileage of the car goes down by 40%. So what we did is, we use a very simple physics phenomenon where we use the carbon materials, because carbon materials have a very high thermal coefficient, but at the same time, these materials are heat dissipating materials. The carbons cannot store the heat. And so imagine you have a carbon nanotube and you apply a very small amount of voltage across the carbon nanotube. So the electric current will start to flow through the carbon nanotube. And because of that electric current, that carbon nanotube will generate a heat. And because the carbon cannot store the heat, carbon starts to radiate the heat in the form of starts to radiate heat in the form of radiations. And we use that technique, and we use that strategy, and we develop some very interesting heaters. So you can see that we develop the heaters which can go to 100 degrees Celsius or even 120 degrees Celsius with when we apply a very small amount of voltage, somewhere around 10 to 12 volts, and the current is somewhere around 15 milliamps. So that's what we are using. So you can twist these heaters, you can fold it, you can even wash them. So it means, like, basically we will wash the car. And these heaters are simply like a stickers, and that can be stick anywhere into the car. So you can stick on the dashboard, you can stick on the car, the internal part of the car, and you can stick it even on the seat. So this is very interesting. But what we learned, so whenever we were actually testing these thermal heaters through the thermal camera, we can see the temperature 100 degrees Celsius. But when we actually touch the heater, the temperature was almost like normal. So the heater was cold. So we were like surprised why it is not like that. And then what we realized is because the heat is in the form of radiations and not the resistive heaters. So you can see, like, we put a very small amount of water on the heater and it actually starts heating it. So what we learned from this is one of the very, very interesting and very safe technology. Because why I'm calling this as a safe, it means, like, imagine if the heater is hot and by mistake if you touch the heater, it is not going to burn your skin. And why is that? Is because the heat is coming in the form of radiation, so it's not a resistive heating system. And that's why we thought maybe this will be a very interesting technology for the defense, because our soldiers, they are into in the field, and they are in the minus temperatures, and we can develop some kind of a heating garments using this type of heating systems. And what we can do is we can have a very small battery, and that battery will do the job. So this is one of the very, very interesting technology which we have developed at QUT. So yeah, this is all about most of our research which we have been doing at QUT. So basically, with the microwave synthesis, we really need to understand if it is whatever the processes or whatever the clean energy technologies which we are proposing, are they really clean? And we really need to understand the sustainable aspect of these manufacturing processes. What we realize is microwave process is really very promising, and it actually help us to synthesize the different materials at with a less energy, but at the same time a very less time. The mechanism of the microwave in solution-based microwave synthesis, the mechanism is very well explored. But in case of a solid-state microwave synthesis, the mechanism is still not very much clear. We know that the material is absorbing the microwave and like generating a lot of heat, so that it can the material that heat is helping material to synthesize. But it is still not clear how fast which materials are useful to be used into these different types of applications. So yes, definitely, I would like to thank all my research group who has been. So this is whatever research I showed you today. So most of my research team has been working for a really very long time, and they are doing a really very great efforts to develop this type of different results. So this is our actually a group photo, and these are all our new team members who has recently joined our research group. So we have a pretty much of a diverse group. We have people from so many different cultures and different countries, even some Sri Lankans. These are two from Sri Lanka. These are two Australians. This is my collaborator from IIT Madras. So Soumyadeep, he's Sudhakar student. He's joining our research team very soon. And these are most of them are like students from Maharashtra. So Mahesh has recently joined as a postdoc. Gaurav is already assistant professor at LBS College Satara. So he recently received this CRB fellowship to visit our research group. Abhishek recently joined as a PhD student, and Shubham is joining next month as a MPhil student. So we have a pretty much of diverse research group. And I would definitely like to thank all my funding partners. Most of our research funding is coming from the different industry partners and Australian government. So from Australian government also, we are getting most of the research, which is for the pilot scale demonstration or commercializing the technologies. So I'm really very much thankful to all of these funding partners who is supporting our research. This is most of our research, which has been highlighted on different cover images. And we are fortunate enough that we could publish very good and interesting research articles in so many high impact factor journals. And I would definitely like to thank again all of you for attending the lecture. And at the same time, I would like to thank again for the organizers for organizing and inviting me to deliver a talk in this interesting conference. So I would be happy to take any of the questions if you have. Thank you again.
Yes, sir, there is a question from the participant. What are the factors and technologies that are there for the safe use of lithium-ion battery? That's a question from the participant.
So in case of lithium-ion batteries, so currently most of the safe technologies which we have been using, they are for the module level. So when it goes to the modules, so we have been using so many different types of electronics or electrical circuits, so that if there is something wrong with the batteries, we can definitely find out. And that is very tricky question. And if you want an honest answer, we still don't have anything which is really very safe to use a lithium-ion battery. And I can give you an example, which is very, very recent example. And I always keep talking about that particular incident which recently happened in Queensland. We have a place here called as Rockhampton, which is 70 to 80 kilometers from Brisbane. And we have Tesla's Gigafactory. So it's a very big, like a battery plant. And what happened in that battery plant is the battery has been exploded, and then whole plant started to burn. There were a lot of firefighters. Everybody was standing there, and they couldn't do anything. They have been instructed that there is no way that you can stop the fire. What you can simply do is just stay there and let everything burn down into the ashes. So that's unfortunate, but that's what is happening. We still don't have that particular safety, aspects. We are exploring. We are looking into different options, but for now, we really don't have anything which we can stop the fire or take care of that lithium-ion batteries. Still very early stage, I would say.
So can we take one more question?
Yeah.
Yeah. It's from Sagar Chaudhary, who is asking what specifications such microwave synthesizers should have. Can we synthesize carbonaceous material in regular microwave synthesizer?
Okay, that's a good question. Okay, not in the regular microwave, because the regular microwave, that is the oven. So what we are using is the customized microwave furnace, and that microwave furnace is something similar to like a conventional tube furnace. But what we do is we maintain the environment. So we have to maintain we have to perform all that experiments in the absence of oxygen. So it means like either in the nitrogen or in the argon. So that is one of the condition. If otherwise, if we do that, if we put that samples into the regular microwave oven, and if we try to do that, everything will turn into the ashes, not into the carbon material, because you are doing the experiments in presence of oxygen. So it will be all smoke out as a carbon dioxide. So it needs to have a specific microwave furnace with a controlled environment.
Okay, sir. And one more question, Satnam Mattu is having. He's asking, sir, can you please explain shuttle effect?
Shuttle effect. What is shuttle effect? So, what exactly mean by shuttle effect?
Okay, so Satnam Mattu, sir, we will share.
Yeah, it would be good
the
if you can.
ID of sir, then so that you can personally email him and ask your queries.
Yes.
Sir, thank you so much, sir, for your insightful lecture, and your expertise has actually clearly given us the great advancement and enhancement of whatever you were talking about on cathode and anode material energy through unique microwave route, which is simple and high yield technology. Thank you, sir. Even from non-physics background, it was interesting to hear your talk, sir. Thank you so much. Now I request Mrs. Nandini Gaikwad, Head of IT Department, to introduce our next resource person, Dr. Rahul Salunke, sir.
Thank you, madam. Good afternoon, one and all. I'm honored to welcome you all to today's international conference and introduce our esteemed speaker for the invited talk, Honorable Dr. Rahul Salunke. He is working at the Indian Institute of Technology, Jammu, as an associate professor. As research concern, his current research interest includes nanoporous materials, sodium-ion batteries, and solid-state batteries for energy storage applications. Today, he brings a wealth of knowledge and experience to our gathering. Throughout his illustrious career, Honorable Dr. Rahul Salunke has been shaping the field through his innovative work in material science. He has published total 97 research papers. He has 3 patents published. The total citation is 13,489 and H index factor is 55. He has been awarded by SERB, Government of India, for Ramanujan Fellowship, also awarded by the Department of Science and Technology, Government of India, for the Inspire Faculty Award. Also received an award of UGC Research Fellowship for the meritorious students in sciences. Today, Honorable Dr. Rahul Salunke will share his insights on the compelling topic of advances in material science, trends and application. Without further ado, please join me in extending a warm welcome to Honorable Dr. Salunke, sir, today. We eagerly anticipate the enlightening speech that is about to be delivered. Thank you. Over to you, sir.
Thank you very much, Nandini ji. So, my voice is audible?
Yes, sir. Hello. Yes, sir. Yes, sir. It's audible.
Okay. So, let me share my screen. So my screen is shared now. Hello, anyone there?
Not yet.
Not yet? Okay, just a moment. Okay, so my screen is now shared.
Yes, sir.
Yeah. Can you see the slides now?
Yes, sir.
Oh, okay. So first of all, I would like to thank the organizers of this conference for providing me an opportunity to deliver this talk. So let me introduce myself. Myself, Dr. Rahul Raghunath Salunke. I am working as an associate professor at Department of Physics, Indian Institute of Technology, Jammu. So for today's this presentation, I am going to deliver a talk about MOF-derived nanoporous the introduction of various energy storage systems. What are the different kinds of the energy storage systems are there? Then I will briefly introduce about the supercapacitors, what are the alternate to the batteries, and the pathway towards the next generation energy storage application. And finally, I will provide the conclusions. So if we consider the green energy storage technologies, today we need a lot of energies from starting from our portable electronics like our gadgets, mobile phones, or the tablets to hybrid plug-in electric vehicles. So variety of places we require batteries or the energy storage that is very useful for our day-to-day applications. So apart from this, there is a large scale energy storage is required where we consider the different kinds of a energy generation systems like solar, wind, grid, and other energy storage, other energy generation technologies that requires a huge amount of energy storage. So if we consider the solar, we cannot get the sunlight all day, or we can not get the wind to the all seasons, or we cannot get the grid supply may be stored somewhere, and for any other use we need to store that energy. So that storage technology is very essential backbone to this success of this kind of a energy generation systems. So let me introduce about the various energy storage systems. There are different kinds of the energy storage system, such as batteries, supercapacitor, or capacitors. We are mainly focused on these three technologies, and out of this, I will mostly focus on the supercapacitor for today's talk. So, if we consider the supercapacitor, so if we consider the supercapacitor, we know that they have a specific energy of around 1 to 10 watt hour per kg. So specific energy defines the ability that how much charge the device can store. That defines its specific energy. Whereas specific power is how quickly the device can release the charge to the external circuit. That defines its specific power. So these are the two important factors in any storage technology. So the storage technologies are limited to supercapacitor. They are in the range of 1 to 10 watt hour per kg for the specific energy, whereas for the specific power it is about 500 to 1000 watt per kg. So if we consider the charge discharge time required, if we consider the profile firstly, in case of a battery, the batteries gets charged very linearly, but the discharge is not linear. It is certain exponential decay. Whereas if we consider the charge and discharge in case of a supercapacitor and the capacitor, we can get a very linear charge and very linear discharge. Where we can see that in case of a supercapacitor, the charging and discharging time varies from few seconds to few minutes, whereas in case of a capacitor, it varies from few 10 raised to minus 6 second to 10 raised to minus 3 second, very few seconds, quickly get charged and quickly get discharged. Whereas in case of a batteries, it takes charging times up from half an hour to 3 hours, whereas discharge time is from 1 to 5 hours because discharge is very slow discharge. And now again, the cycle life is the last factor. If we consider the cycle life of batteries is about 500 to 1000 cycles. That means that after the certain cycling performance, the battery performance get degraded because of the material frustration or any other chemical changes occurred in the battery performance gets degraded with time. Whereas in case of a supercapacitor, we can sufficiently go over 5 lakh cycles of charge discharge. That means their lifetime is much more higher compared to that of the battery systems. And in case of a capacitor that we use in our normal electronics, we know that they have an infinite charge discharge time. So huge number of cycles we can charge and discharge these kind of devices. So this is the basic difference between these three kind of devices. Now, if we move forward, then for the supercapacitor, so first we start with the supercapacitor basic. So based on the charge storage mechanism, supercapacitors can be divided into two different types. One is a pseudo-capacitor and another is known as the electrical double layer capacitors. So for this presentation, we are going to focus on the EDLC type materials because which only is a surface region. That means that the charge can be stored only at the surface of the material. So here is a positive and negative charges are placed. If there is a negative charge, the positive ions from the electrolyte comes to the surface of the material and get adsorbed on the surface of the material, and then electrical double layer is formed. One is inside the material, one is outside, and because of that the charge gets stored, and because of that this type of a capacitors are called as a electric double layer capacitors. So the physical storage, safe, non-toxic, low loss, fast charge discharge, and long cycle life. These are the important characteristics of this kind of a characteristic of this kind of a electrical double layer capacitors. So unlike to the conventional capacitors, which have a capacity of around a few microfarads, this type of a supercapacitors can have capacity up to in terms of a farad. Hundreds of farad we can achieve by use of this kind of a technology. This is usually contain two electrodes, as we have seen. These are the two electrodes, and they are separated by a electrolyte. So electrolyte is basically any aqueous medium or any organic medium that can be possible to vary. For the commercial application, mostly organic electrolytes are used. So the companies like various companies are there, like for the non-aqueous electrolytes, like Nippon Chemicals Con and Cooper and Ness. These kind of a companies develop this kind of a supercapacitors, and they are very useful for very commercial applications. So now let's look at the different charge storage mechanisms. So how the charge gets stored on the surface of the material. So there are various different charge storage mechanisms. In the case of a carbon, if we consider a carbon, it may be a sphere, it may be a graphite, or it may be a nanotube. or a porous carbon material, negative ions are adsorbed on the surface of the material and electrical double layer is formed, and thus the charge gets stored on the surface of the material, as we can see in this figure. So, and in this case of a electrical double layer capacitors, the charging and discharging, we can get a very rectangular shape. There is no any redox peaks can be observed, because the mostly charge is a electrical double layer is formed on the surface. There is no redox reaction is occurring in the material. So the charge comes, get adsorbed on the surface of the material and get deadsorbed. And because of that, a very rectangular CV shape we can obtain in case of a electric double layer capacitors. Whereas in case of a pseudo capacitors, if we consider another type of a capacitor, the ions can intercalate inside the materials, and because of that, they form certain redox reaction inside the material. They form some certain kind of a electron exchange reactions, and because of that, some redox reactions happen on the surface of the material, few layers of the material, and because of that, some oxidation and reduction peaks can be observed as seen in this CV shape figure F. So where the example of this kind of a pseudo capacitors are certain metal oxides like manganese oxides or the ruthenium oxide. So these kind of a materials can have certain kind of a redox reactions, and because of that, the charge gets stored. The disadvantage is that as there are certain number of redox reactions are continuously occurring to the surface of the material, after certain cycles, the performance of these materials get degraded, and because of that, their performance quickly get these kind of a capacitors quickly get discharged after certain number of cycles. So their performance cannot be retained for over a long cycle of time, like as we have seen in case of a electric double layer capacitors. So there is another type of a intercalation and deintercalation type materials where the ions get intercalated and deintercalated and the charge gets stored. So these are the basic charge storage mechanisms possible for the supercapacitors. Whereas we have seen that if our sample is of the 50 nanometer thickness or it is a bulk, depending upon what kind of a sample thickness is there, the discharge profile can be observed. For the small thickness, the more charge can be stored because more surface area is accessible to the electrolyte ions. Whereas in case of a bulk, there is a certain dead weight is possible, but that is not accessible to the electrolytes, and because of that, less charge can be stored. On the other hand, if we see a battery type materials, there is a plateau we can observe. When we see the discharge curve of this kind of a batteries, we can see a strong plateau in case of a discharge profile. Whereas if we go to the smaller thickness, then very linear, slightly linear discharge profile can be observed. So this depends upon how much thickness. That's why in battery mostly prefer that we should use a large amount of mass so that that will show the actual material characteristics in case of a battery materials. Also, if we see the galvanostatic discharge profile, we will observe that for EDLC material, discharge is not a linear. EDLC material discharge is not a linear for the bulk and for in the thin film form, but the plateau is observed for the for in voltages for the bulk battery material. That is it sustains a linear voltage up to a certain time. So this is about the charge discharge mechanism. And if we go about the electrochemical supercapacitors, then we can see that electrochemical, up to now we have seen that electrochemical supercapacitors are intermediate between batteries and capacitors. They have high power density, long cycle life, and they are safe in operation and they are recyclable. And the present focus is that, so what's the catch in the capacitor research is that how we can improve their energy density so that they can be comparable to that of the battery systems. So if we can replace this kind of a capacitor with the battery energy density, we can use them in large number of application. Because of that, we can get in different kinds of application that are not possible for the normal supercapacitors. So this is the goal for the electrochemical supercapacitor research. Now, presently there are different types of the carbon materials for energy storage, like graphene, fullerene, nanotubes, diamond, amorphous, and graphite. They can be divided into various forms, like sp1 bonded carbons, like carbenes. They are the linear chain of the carbons, whereas there are sp2 bonded carbons, like graphene, nanotubes, nanohorns, nanocones, fullerene, carbon onions. On the other hand, we have various porous or disordered carbon materials like templated carbon, carbide-derived carbons, activated carbons, carbon fibers, and aerogels. So, variety of carbon materials are possible. On the other hand, we have sp3 bonded carbons like nanodiamonds. But the carbon that is most commonly used for the electrochemical application are focused on the sp2 bonded carbons, because the free electron associated with this pi bond is able to carry the charge, and because of that they have a very good conductivity compared to that of the sp1 and sp3 bonded carbons. Although we have this kind of a variety of carbon materials, and graphene is a mother of all graphitic materials. Like they can be wrapped into zero-dimensional bulky balls, as we can see here. They can be wrapped to form a zero-dimensional bulky balls. They can be rolled to form the CNTs. They can be stacked to form a graphite, or they can be introduced some kind of a pentagonal defects to form a fullerene. So, although we have variety of carbon materials and graphitic carbon material, every family has an enormous richness in its structure, and every dimension is useful for certain specific application. But still, the material that is most commonly used for the commercial application is a activated carbon. As we can see, because the activated carbon, or a very cheap carbon, we can see that it has a very highly commercialized carbon, and it is made from a cellulosic material like coal, wood, or a coconut shell. So they can be easily formed. Just burn this material, give some chemical treatment and heating treatment, or the activation by a chemical treatment, then they form a tons of quantity of a activated carbon. They readily have a very high surface area of around 3000 meters square per gram or more, and they have a very large micropore structure that is very important for achieving a high energy density that I will discuss in the next few slides. So this is the advantages of the activated carbon material that is commercially available. Although we have this kind of a commercially activated carbon, still people are trying to develop different kinds of the carbon materials, and one of these type of a carbon is called as a MOF derived carbon. MOF stands for a metal organic framework. So metal organic framework is very simple in synthesis. As we can see, these are the metal precursor and these are the linkers, maybe 2-methylamidazole you can say in this case. And we can see that just to disperse these linkers with the metal ions, and they form a link, and because of that coordination they form a metal organic framework. Now, after a controlling annealing in the nitrogen environment and the air atmosphere, we can convert this kind of a metal organic framework into either a porous carbon or a metal oxide. Because of that, they have a very simple synthesis. This, as I have illustrated here, they have a very simple synthesis method. They have a controllable size. So what kind of a linker you are going to use, what kind of a metal ion you are going to use, that will decide what is the shape of that metal organic framework, or what is the surface area, what is the pore size distribution, so what is the micropore structure, that we can decide by use of these kind of precursors. So we can control micropore to mesopore ratio depending upon application. So what kind of a application we are going to use? So we are going to use it for supercapacitor, we are going to use it for battery, or we are going to use it for any other application. Depending upon what is our target application, we can design this kind of a MOFs, and there are more than about 20,000 well-known MOFs. So you just change the linker and you just change the metal ions. So depending upon the combinations, there are up to now more than 20,000 well-known MOFs reported in the literature. And because they can achieve a very high surface area, they are very fascinated to various application fields like sensors, solar cells, batteries, supercapacitors, catalysis, or any other application you can take. These materials are very fascinating for these kind of applications. So as we can see that based upon our synthesis method, we can control the surface area, pore size distribution, and what kind of a temperature we are going to optimize for this kind of a material. That will decide how we will get the surface area or the pore structure of this kind of a material. So if we can improve this performance of the supercapacitor by using this MOF, we can achieve, if we have a very narrow pore size distribution and in the micropore region and a wide pore distribution in the mesoporous region, then this kind of a pore structure we can use for various application of the supercapacitor, and because of that we can improve the supercapacitor performance. And if we can improve the supercapacitor performance, we can use it in many different applications, such as trams in Germany. They are powered by supercapacitors, which use 30% of the less energy than the equivalents in the other region. We can see that if they use supercapacitors, they get charged very quickly, and because of that, they have a 30% energy efficiency compared to that of their other equivalents in other region. Whereas if we take another example, like a bus transport at the airport, this is one I have taken from the web page, and it is a bus transport in Shanghai airport. We can see that this kind of a charger is there on the top of the bus, and the supercapacitor array is placed downside. And when the bus gets stopped, people get on and off the bus, and during this time the bus gets charged and it is ready to run for another 5 kilometers. So because it is quickly charging and it is a maintenance free, we can use this kind of a bus for unlimited times of cycles, right? And because of that, our cycle life will, because of this improved cycle life of the supercapacitors, we can use this kind of a bus transport for the small distances, and we can develop this kind of a supercapacitor array for this kind of a bus. So these are the few advantages of this. Now the question is that how one can improve the energy density. So the energy density, how we can improve. So that answer can be given by our, first we will start with our parallel plate capacitor model. In case of a parallel plate capacitor model, we know that if our material is negatively charged, then ions get adsorbed on the surface of the material and the charge gets stored. Whereas if our material is a porous material, so if the micropore structure is available, then the ions go inside the material. So our material is a negatively charged and the ions get inside the materials. And large number of interactions are possible because the ions are inside as well as outside, and thus more number of ions can interact with the pore structure as well as the outer surface, and because of that the charge storage is more effective. This is the some kind of a breakthrough research is done by some scientists in science and reported in Science and Guante, and there are certain simulation studies also, molecular dynamics and DFT studies also reported, and they found that if the pore size decreases below less than 2 nanometer, then the supercapacitor performance increases abruptly. And whereas as we go on increasing the pore size, the performance gets stable to a certain value, whereas below this we can get a very abrupt increase in the capacitance. That means that ion dissolution into sub-nanometer pores is very essential for improving the supercapacitor performance. On the other hand, if we see by this model, we can see that these are the pores in on the surface of the material. We can see that this is a typical pore structure, and this is our gray shaded area is our material, and this is a positively charged. Now, if the pore size is very large, we can see that the ions get adsorbed on the surface of the material, and very near to the surface, they can effectively interact with this material, and because of that, interaction are little bit weak for this kind of a far placed ions. Whereas as we go on decreasing the pore size 2 to 50 nanometer, we can see that now they get aligned to the surface. Now the interaction becomes quite active within these pores, and when the ion size now matching with the pore size, now they get aligned to the surface of the material, and because of that, more charge can be stored, and more interaction can be possible, and more charge can be stored. And because of that, when our pore size is less than 2 nanometer, we can achieve a very good capacitance as predicted by the theoretical and experimental model. Because of that, this very first requirement is that the micropore structure and that the ion size should be matches with the pore size. When the ion size matches with the pore size, we can achieve a very high capacity for the any electrochemical device. This is not only true for the carbon materials or any kind of a non-aqueous electrolyte. This is possible for the H2SO4 as well as any other metal oxide. So if we take any material with the matching pore size with the electrolyte, then your performance is going to be very high. So this is the basic principle for improving the energy density of supercapacitors. Now on the other side, there are various types of the electrolytes. So we know that energy density is equal to 1/2 CV square, and it is proportional to the voltage window. So what kind of a voltage window? It is a 1 volt, it is a 2 volt, it is a 3 volt. Depending upon the voltage window, our energy density will go on increasing. But problem is that in case of a aqueous electrolyte, we cannot go beyond 2 volt, because whatever the potential of 2 electrodes, we cannot go beyond that. And that's why in case of a aqueous electrolytes, we can go up to maximum of 2 volt. Whereas in case of a organic electrolytes, we can go up to 4 volt, and in case of a ionic liquid electrolyte, this is the ideal one I am telling. So up to 5 volt is possible. So the choice of a proper electrolyte is very important in achieving the high energy density. The conductivities of the electrolyte, aqueous, organic, or the ionic liquid, aqueous electrolytes have very high compared to that of the organic or the ionic liquids. The use of the asymmetric supercapacitors, ionic liquids, to extend the potential window make it comparable to that of the battery materials. So there are certain reports in literature also, they can achieve energy density up to 60 or 80 watt hour per kg, but still research is going on in this direction to how these kind of a materials can be commercialized, or how their cycle life performance, that are the very important things to consider for the commercial level application. So up to now we have discussed that your ion size should match with the pore size. That is very essential to improve your performance. So materials need to be developed in the micropore structure form. So metal organic form frameworks are very essential for this kind of a work. And on the other side, we have seen the role of various kinds of the electrolytes. So choose right electrolytes so that we can improve the potential window or the energy density of that materials. So we don't skip this one. So there are various approaches for the capacitor application. In our work, we have developed various types of the approaches for the capacitor applications. We have used single MOP, bimetallic MOP, core shell MOPs, and optimal thermal treatment that leads to achieve us various MOP-derived porous carbon materials. They have a very high surface area, controllable porous architecture tunable composition and the tunable microstructure. So this is very essential for our applications, and that's why we can use it in the asymmetric as well as symmetric form, and to ultimately achieve a very high supercapacitor performance. So this is just the outline of what kind of approaches we have utilized in our work for achieving the high performance. So I will explain one by one these approaches. So let's first start with this basic MOF-derived carbon materials. So typically zinc acetate and 2-methylamidazole precursors were used, and by co-precipitation we get the metal organic framework ZIP-derived carbons, and this is called as a ZIP-8 typically because it contains zinc and 2-methylamidazole. So there are different names are available: ZIP-8, ZIP-67, ZIP-62, ZIP-61. Many series of materials are there depending upon what is the linker and what is the metal oxide. Depending upon that, there are various names are available in the literature. But for today, we are just starting with the simple ZIP-8 nanoporous carbon, ZIP-8 derived nanoporous carbon, and this is very simple and very commonly used, and it has a very stable porous structure. So if we consider ZIP-8 and ZIP-67, they have a very highly stabilized porous structure, and because of that, their porous structure could not collapse. When we use in the electrolyte system, this porous structure should not collapse, and this is a very typical requirement of any kind of application, and that's why ZIP-8 and ZIP-67 are most commonly used these nanoporous carbon materials. And this is a very simple synthesis, and because of that we got a typical surface area. So BET MOF derived carbon have very highly stable porous structure, high surface area, and can be changed to depending upon the synthetic condition, what kind of a synthetic condition you use, what kind of a heating temperature you are going to use. Depending upon that, this porous structure can change. So ZIP-8 derived carbon have shown a very stable porous structure with a surface area of around 1610 meters square per gram. So this is very essential for any kind of a supercapacitor application, and we can see that they have a very good micropore structure, and if we see closely, most of the micropores lie in the range of the most of the pores lie in the range of the micropore. So the total micropore volume in this case is 59%. So that means that 59% of the micropores are in the range of the micropore region, and the other pores are in the mesoporous region. So this is the typical morphology of our samples. The morphological analysis of this sample show that that they have average particle size of around 1 micrometer. So we can see that further high magnification SEM confirms that the nanoporous carbon shows a symmetric geometry with a polyhedron type shape, and even the particle size of this kind of a particles can be controlled by changing the reaction conditions. Sorry to interrupt. I just want to confirm that am I audible? Okay, everything is okay.
Yes, sir, you are audible.
Yeah.
And your pipette is quite visible. Yes, sir.
Okay, thank you very much. Yeah. So even the particle size of this kind of a particle can vary from 300 to 5 micrometer. By changing the reaction conditions, we can change the size of this kind of a particle. The HRTM shows the formation of the micropores. Further HRTM I will show the actual pore structure also. So this is a STM HADF STM image, and we can see that from this TM elemental mapping, we can see that 85% is atomic percent is a carbon, and 15 atomic percent is a nitrogen. So this is the typical normal MOF derived carbon material looks like. And if we see the structural analysis, we can see that there are more majorly 2 peaks associated with 002 and very small peak here. We can see that, and it represents a graphitic type of a carbon, whereas Raman analysis show D band and G band. If we consider a zip-8 carbon, it is highly porous and amorphous type of a structure, whereas if we take zip-67, where it is a metal source is a cobalt, it leads to formation of a graphitic degree in this kind of a carbon, and because of that the surface area might be little low, but the graphitic degree or the conductivity associated with this kind of a polyhedra is very high, and because of that they have a high graphitic degree. G band associated with the Raman spectra have high intensity compared to that of the zip-8 carbon. So this is the typical supercapacitor performance. We can see that they have a very rectangular CV shape, and we can see that as we go vary the scan rate, even up to 1000 millihole per second, from 5 millivolt to 1000 millivolt, there is not much loss in the capacity. We can see that up to 120 farad per gram we can easily achieve with this kind of a scan rate variation. We have varied the electrode mass loading, and we can see that the capacitance retention goes on increasing as we increase the mass loading, but the capacity is slightly less because the accessible surface area to the electrolyte ions is little bit lower, and because of that the capacity starts degrading. So this is the typical characteristic, and now we have used this kind of a carbon in the two electrode configuration in the aqueous electrolyte like in H2SO4, and we can see that on one side we have MOF derived nanoporous carbon, on the other side also MOF derived nanoporous carbon. With a H2SO4 electrolyte we can get the very CV shape up to 0.9 volt maximum we can go, because there is a limitation of the potential window. They can have very limited specific energy and specific power. Now, to further enhance the electrochemical performance, the device study using the organic electrolytes, we have developed certain this kind of a Hoshin cell type the supercapacitor testing assembly, and this is the typical structure where on the both sides we have a current collector, nanoporous carbon. This is a typically structure of this kind of a carbon coated on the stainless steel substrate, and here is the cross section of this kind of a thing, and we can see that it is this kind of a nanoporous carbon coated on the current collectors, and they are placed separated by a separator and the electrolyte, and this whole assembly is put in the Hoshin cell, and we have measured this kind of a performance in organic electrolyte NETABF4 in propylene carbonate. And we can see that now we can go up to 2.4 volt with 10 millivolt per second, and this is 100 millivolt per second. We can see that the shape is quite good, retained very nicely up to 500 millivolt per second. And when we calculate the stack capacitance, that is the volumetric capacitance, we can see that the volumetric capacitance is around 10 farad per centimeter square compared to that of the if we compare this from the impedance analysis, depending upon the frequency we use, we can calculate the stack capacitance, and the stack capacity is observed to be nearly about the same 10 farad per centimeter cube. So when we compare our performance with respect to energy density and power density, now we are changing the term to the density, because this is a volumetric capacitance, and because of that we can safely say it is a density. When we use the mass of the material, we should say specific energy and specific power, but when we use the volume of the material, we should say density. This is very important terms in the electrochemical field. So if we see our work, we can see that our work has got very comparably high performance compared to that of the lithium thin film battery electrolyte capacitors or the carbon onion capacitors. But we can see that these carbon onion capacitors have very high specific power. Now, power density, if we see this power density, because they have the zero dimensional, the ions comes and go very easily, abruptly on the surface of the material. That's why our material is hard to beat this kind of a carbon onions, which is a three-dimensional. Our material is a three-dimensional material, and it's very difficult to remove the ions very quickly compared to that of the carbon anion materials. And any other commercial materials, magazine, RGO. So we have compared the performance with all types of the materials, and we have seen that our performance is comparatively higher than that of the other material. This is a commercially available activated carbon. This is from A1 Taiwan company, and we have compared this performance with this kind of a activated carbon also. Although this kind of activated carbons have micropore structure around 74%, but still this kind of a carbons have very limited conductivity, and because of that our material has shown comparatively high performance than that of the activated carbon materials. Now another important problem was stacking of the composite. When we coat the material on the surface of the plate, the material gets stacked on the surface of the material, and because of that the ions cannot access the material very easily, and because of this stacking problem most of the materials performance get degraded when they coated on the stainless steel substrate or any current collector. So this was the basic problem. To avoid this problem, we have utilized our nanoporous carbon. So we have prepared this nanoporous carbon, and we try to coat it with the aniline monomer, and we try to develop a polyaniline. So polyaniline nanorods are grown on the surface of the material. As we can see from this SEM image, very nice uniform coating of this polyaniline nanorods on the surface of the material can be possible. Now the advantage is that these polyaniline nanorods have very high conductivity, and backbone is a porous carbon with the ion diffusion. So a fast electron transfer, excellent ion diffusion, and high performance for the supercapacitor can be realized by use of this kind of a structure. So these are the various time differences. We have prepared the samples for 1 hour, 2 hour, 3 hour, 4 hour, and 5 hour aniline coating. And we have developed this kind of a various TM images, and we observed that this nanorod length goes on increasing, and the density goes on increasing as we go on increasing the time. So we can see that very uniform coating in case of this 3 hour, and after 3 hours the material gets stacked on the surface of the material. It is coating the surface, and that's how it is blocking the inside material, and because of that some problems occur in this kind of a 4 hour and 5 hour samples. So various characterization techniques like XRD, Raman spectroscopy, and the FTIR analysis are confirmed to confirm the coating of this polyaniline on the surface of the material and the thickness variation that we have carried out this kind of analysis. And we observed that for the 3 hour thickness, we can see that very uniform coating can be observed, and these polyaniline nanorods can be seen on the surface of the material. Now we can clearly see this reflection in the electrochemical studies also. We can see that very rectangular CB shape in case of a carbon, whereas in case of a polyaniline, some redox peaks can be observed. Of course, polyaniline is a redox material, and because of that, certain redox peaks can be observed. Whereas if we use this carbon-coated polyaniline, we can get a very rectangular shape of the carbon backbone, as well as the redox peaks associated with the polyaniline. And because of these advantages, the CV shape is improved, and we can get a very high capacity of around 1100 farad per gram. So we can see that 57% retention is possible with this kind of a materials, whereas in case of a EDLC or the carbon-based materials, only 68% retention was there. And in case of a polyaniline, it was 39%. So this is the slight difference in the retention of this kind of a materials. Now we have used this kind of a carbon material for our device application, and we can see that our carbon polymer system achieves a very good specific power and specific energy compared to that of the activated carbon or the carbon based materials. In another approach, now we have a amorphous carbon. So if we consider zinc ions and methylamidazole, we can get a ZIP8 network. The advantages with this kind of a carbon is that they have very high surface area, over 1500 meters square per gram, and they have a very high nitrogen content. Whereas their disadvantage is that it is very amorphous nature, and it has a less stability. These are the advantages associated with this kind of a carbon. On the other hand, we have another carbon, that is cobalt ion based carbon and 2-methylamidazole. It is called as a ZIP67 carbon. ZIP67 derived carbon, and it has advantages of high crystallinity because of the cobalt, the good graphitic degree, good conductivity, and good stability is possible. But they have disadvantages of the low surface area and low nitrogen content. Now we try to fuse these advantages into one material by coating this kind of we use ZIP8 as a seed, and we try to coat it with the ZIP67 material. And because of that coating, we got a nanoporous carbon coated on the a nanoporous carbon inside and the graphitic carbon coated on the outside. So we try to fuse the advantages of these two types of the carbons into one material by use of this work. So we can see that this is the elemental spectra. We can see that outside material and inside material. And now we can confirm the thickness, what kind of a thickness we can grow of this ZIP67 on the ZIP8 carbon. So we try to coat various thicknesses, and inside material is a porous carbon and outside material is a graphitic carbon. And because of that, we can improve the capacitance performance in our sample. We try to vary the thickness of this coating, and we try to vary the performance in case of a core shell samples. In very another interesting approach, we try to utilize this kind of a single MOF derived nanoporous carbon to develop two different materials. So when we heat, our interesting fact of our ZIP67 material is that if we heat this material in nitrogen atmosphere and provides a HF treatment, it leads to form a nanoporous carbon material. And these nanopores are the high graphitic nature, and these are the pores on the surface of the material. We can see that. On the other hand, if we heat our material at optimized temperature of 500 degrees centigrade in nitrogen, so if we directly heat our material in air atmosphere, the structure collapse. That's why we first retain this structure by heating this material in nitrogen atmosphere, and that's how we can retain the shape of this original parent MOF. And when we heat it at 350 degrees centigrade in air, the outside material is a nanocrystalline metal oxide or the nanoporous metal oxide, we can say that. So if we see the HRTM images, very high fringes or crystalline fringes can be observed on this kind of a nanogranular surface. Whereas if we heat in the nitrogen environment only, we can get the nanoporous carbon with highly pores on the surface of the material. So in case of a asymmetric supercapacitor, we typically use activated carbon as a counter electrode. Whereas in this study, we try to develop two kinds of the material from one parent MOF, and we try to use it for the supercapacitor application. So this is a typical structural analysis. We can see that this is a selected area electron diffraction pattern, and we can see that two peaks associated with a graphitic carbon can be observed. Whereas in case of a metal oxide, we can see that different peaks associated with the metal oxides can be observed in HRTM as well as the XRD analysis. So again, several supporting studies have been carried out to define the ratios of cobalt, oxygen, carbon, and nitrogen in this kind of a carbon and cobalt oxide. And we have seen that in case of a carbon, there is a carbon percentage is 90%, whereas in case of a cobalt oxide, carbon percentage is 1.7%. Whereas in case of a cobalt oxide, cobalt and oxygen percentage is very high compared to that of this carbon and nitrogen percentage. Where similarly, TM elemental mapping is also carried out to study the different kind of the elements present in the material. These are the surface area analysis, and surface area analysis also confirm that the cobalt oxide polyhedrons prepared by use of this method have very high surface area than the other reported materials like ultra-layered cobalt oxide nanosheets, cobalt oxide nanorods, or any kind of a method or the material of cobalt oxide developed by using any other method. Our method gives a very high surface area for the supercapacitor application. Because of this, we have carried out the electrochemical analysis and we observed that 52% retention for the cobalt oxide and 40% retention for the carbon material. Now we have on one side cobalt oxide and the other side zip derived carbon, and which is having a very good conductivity, high surface area, good stability, and that's why we have used this kind of a asymmetric combination and achieved a very good specific capacity of around 100 farad per gram. So this is the Ragon plot performance of comparison. We can achieve a capacity, a specific energy of around 36 watt hour per kg, which is much higher than that of the other nickel or the other polymer-based materials. In one very another interesting approach, we try to develop this kind of a material into two-dimensional form. In the two-dimensional form, what we did is that we try to develop a graphene sheet, and on the graphene sheet, we try to link this kind of a imidazole linkers, and on that imidazole linkers, we develop this kind of a cobalt-based MOF. And so now we have one graphitic layer of the graphene, and on the other top there is a cobalt-based MOF, and because of that, layered heterostructures can be generated. And after carbonation and washing, we get 2D graphitic nanoporous carbon materials. So this is very interesting study because up to now we are getting 3D carbon materials, and now we have developed into the 2D carbon materials. So the morphological analysis indicate that. So these are the porous carbon materials, and we can see that the pores are generated on the surface of the material, and 2D layers of the graphitic carbon and the MOF derived carbon can be seen on the surface of the materials. So we have shown many studies to prove that the graphitic degree of this kind of a materials is improved in case of a 2D heterostructures. So structural investigations have been carried out to study the XRD, Raman, different and XP studies prove this kind of a conformation of this kind of a heterostructure materials. So we have developed a device associated with that, and we can vary the potential window from 0 to 2.5 volt, and we can get a very high capacity. The cell capacitance was around 22 farad per gram, and the specific energy of around much more compared to that of the other commercial associated devices. So this is the lead acid battery performance. So we can see that our energy density of around 20 watt hour per kg specific energy. So like this way, this method is not only limited to the carbon materials, but also various types of the metal oxides can be prepared by use of this kind of a method. So various metal oxides, mixed metal oxides can be prepared by use of this kind of a technique. So we can design different kind of a one-dimensional, two-dimensional, or a three-dimensional material. By selecting a suitable precursor and parent MOF, one can design desired material. The dimension is important parameter of the material that can decide the electrochemical interaction possible for achieving the energy density and power density. So this is not only limited to the EDLC type. Now further focus is that how one can improve the energy density. So there are various approaches like hybrid capacitors using lithium titanate. One can achieve the energy density up to 15 watt hour per kg, whereas lean lithium titanate, because of the TR, the weight of the device is very high. So further people introduce the lithium ion capacitor using graphite anode. That means that this is a battery type material, but there is no lithium inserted. So on one side there is a graphite, on the other side there is activated carbon. So graphite is a lithiated graphite, and because of that the energy density of this kind of a device is about 40 to 60 watt hour per kg. And nowadays people are developing these MOF derived materials because of this pore structure and the lithium storage ability. We can achieve a capacity of around 100 watt hour per kg. Although I have certain results with me, but they are still yet to publish, and that's why we are working on that. So next generation lithium ion capacitor technology is that we can achieve a capacity up to 100 watt hour per kg. So recent studies on lithium ion capacitor have shown that these capacitors can possible to achieve the energy density more than 100 watt hour per kg. That means that we can go up to 100 to 120 watt hour per kg, and that is much comparable to that of the battery type of a material. Such a technology is very useful for the hybrid electromobility vehicles and the fast charging requirement, because of course the supercapacitors allow the fast charging, and this is very important for the next generation technology. So this is the typical development of the lithium ion capacitor, and that is all for today. And today I will stop at this point. So thank you very much. Thank you.
Thank you, sir. Thank you, sir, for the wonderful presentation, sir. Thank you so much. Sir, can we take few questions?
Yeah, please.
We have few questions from the participants, sir. The first question is, how different pores store charges at different rate, specifically at very low rate or frequency, and at very high rate and frequency, like 10 millivolts per second or 100 volts per second?
Okay, so depending upon what kind of a scan rate you are going to use, so obviously at low scan speeds, the ions get a sufficient time to intercalate and deintercalate into the material. So the material, so ions can go deep inside the pores and the charge can be stored. But at the highest scan speeds, the ions cannot get sufficient time. So that means that you are moving the ion, but you are not providing him time to go inside the pore and sufficiently store the charge, and that's why you have seen that as the scan rate goes on increasing, your capacity goes on decreasing. That means that it is not possible for if we use small pores or the micro pores, it is not possible to store large amount of charge at the highest scan rate. It is not possible.
Okay, I hope that resolves the question. One more question is like how dissolution can be controlled for fast insertion of ions within the electrode pores?
That is the same thing. So if we want to dissolve more ions, you should have micropore structure. And again, if we have you can use some sort of a hybrid structure. So 50% micropores and 50% mesopores. In that way, you can, at the high scan speeds also, you can have a good storage. Retention may be very good if we have a proper ratio or proper balance of the micropore and mesopores. So in that way, at high scan speeds, mesopores are helpful. At the low scan speeds, micropores are very essential. So in that way, we can balance the charge storage at the higher and the low scan speeds.
Okay. One more question is from Shivani Gawande. She's asking, please let us know the accurate method for measuring active material mass needed during specific capacitance calculation.
Okay. You meant to say we have to take the whole device mass or some sort of a, I don't know what she's asking about.
Yeah. Okay.
Yes.
Okay, I think we can't take all the questions. There are a few more coming up right now. Okay, so we end up here, sir. Thank you so much for your valuable presentations. And you have.
Hello.
Yeah, if you have any certain specific questions, you can
May I ask a question?
Yeah, please. Yeah. Hello.
Yes, somebody is trying to ask questions.
Hello.
Satna?
Yeah, Satna.
Hello.
Yes, somebody is trying to ask questions.
Yes, sir. Yes, sir. I want to ask one question. Sir, in a particular case, when we test one single MOF with different types of electrolytes, we get different types of capacitance. For example, say ZIF, if it has ZIF in different electrolytes like KOH, LiOH, or NaOH.
Yeah.
So we'll get different types of capacitances.
Yes.
So my question is, there are certain parameters which decides the capacitance when we change the electrolytes. Actually, I want to know about it.
Obviously, first of all, it is the electrochemical. Sorry, my voice is repeating again. Can you mute your audio, please? Hello? Yeah. So obviously, first of all, electrochemical potential is the important thing. So, and secondly, the pore size, the ion size. So maybe K plus have different size, Na2SO4, Na ions have different size, H plus ions maybe have different size. So how this size is very essential. So if that will successfully intercalate or de-intercalate into the pores, so that will define the you, how much charge you can store in with a specific electrolyte. So that is the yeah.
So in my case, actually, according to size, actually I get into the size thing firstly. So according to size, K plus ion has the biggest size, then Na plus ion, and then Li plus ion. So
Yeah.
the capacitance should be like more for KOH, then for NOH, and then for LiOH. But surprising.
Potential window provided by the electrolyte is also important thing.
Uh, Sorry, sir.
So suppose your potential window for KOH electrolyte is from 0 to 0 to 0.6 volt.
Yes, sir. It's 1.5, 0 to 1.5.
So you're talking about two.
No, sir. 3 electrode system.
How three electrode is possible? Because in aqueous electrolyte, oxygen and hydrogen evolution will occur at 1.3.
So, sorry, sir. Sorry. It was for 2 electrode. Yeah, it is 0.5 only.
So
0 to 0.5.
So and in a case of from minus
Minus
0.9.
0. Yes, sir. Yes.
So obviously the potential will be higher and you are getting more capacity in
Madam,
Yes, sir.
madam, later on, since our next resource person is waiting. I'm sorry to interrupt, ma'am.
Sure, sir. Sir, can you, may I mail you?
Yes, sir.
Yeah, surely. Yeah, please contact me.
That you can share some research.
Yeah.
Yes.
Sir.
Thank you. Thank you
Thank
so
you
much,
very
sir, for your valuable presentation, sir. Your presentation has emphasized on the fundamentals of electrochemical energy storage devices and electrodes, especially of carbon material for application of supercapacitors. Also, you have given a deep insight on metal organic framework based material engineering for supercapacitor application. So thank you so much for accepting our invitations and giving your precious time for this conference, sir. So thank you so much, sir.
Thank you very much.
And now I request Dr. Nitin Sasane from Department of Chemistry, Assistant Professor, to introduce our next resource person, Professor Rupesh Devan. Over to you, sir. Nitin Sasane, sir.
Thank you very much, madam.
Yes,
May I
sir.
audible? So very good afternoon to one and all. I am going to introduce Professor Rupesh Devan, sir. Dr. Rupesh Devan is a professor in Department of Metallurgical Engineering and Material Science, adjunct faculty at Civics and Department of Chemical Engineering, IIT Indore. He joined IIT Indore as assistant professor in March 2017. He postgraduated in physics and awarded PhD in 2007 in physics from Shivaji University, Kolhapur. He is recipient of DUO India Professor Fellowship Award and Inspire Faculty Award by DST India. He has served as associate professor at Central University of Punjab in 2016-17. He is also Inspire faculty at Pune University from 2014. Okay, he is the editor of the Chinese Journal of Physics, also guest editor of the special issues Journal of Nanomaterials and Material Today Proceeding. His research is focused on nano-hetero-architectures and core shell nanostructures for energy storage, conversion of photoactive materials for solar supercapacitors, water splitting, and desalination. In his research field, he has published one book, two book chapters, three special issues, and 130 research articles in international journals, having citation more than 6,500, H index 48, and I-10 index 104. He has many awards, honors and award in his credit. I am going to read few. Best Research Paper Award, Outstanding Researcher in Material Science by Venus International Foundation. He is listed in the world ranking of top 2 most influential scientists by Stanford University uh, uh, in 2021, 22, and 23. He has completed 6 research projects, rupees 1 doing the research project for, and he has of 3 crore 28 lakh rupees. Under his guidance, four PhD students awarded the PhD degree, one has submitted PhD thesis, and 7 students pursuing PhD degree under the able guidance of Dr. Rupesh Diwan sir. Now, with this brief introduction, I request Professor Dr. Rupesh Diwan sir to deliver his invited talk. Over to you, sir. Hello, may I audible, madam?
Yes.
Okay.
Dr. Rupesh Diwan sir, you may please continue with your invited talk. Please unmute yourself, sir. Unmute kara. So please give us a moment.
Am I audible?
Yes, sir.
Okay, let me share the screen because I'm getting message that you have been controlled, so I'm not able to share the screen.
Yes, sir.
So give me a time. So and let me share the screen.
So you can now share your screen, sir. There's an arrow below. Present now.
So can you see the screen?
Yes, yes, yes.
Okay.
Visible, sir.
Okay, good. So let me open the pointer. Okay, that's good. So shall I start?
Yes, sir. Yes, sir, sure.
Yeah, okay, thank you. Yeah. Since morning you might be hearing 2 lectures. Just
Yes.
Rahul has given, who is my very close friend. And Rahul has talked about supercapacitors. That's really great to hear him after a long time. So here I'm going to talk about designing nano-hetero architectures for future energy application. Because energy is more important nowadays. Of course, I have included some display devices. Why? because right now you're watching me on a display. That means you're watching me either on a computer or your cell phone. So if you go back to the history, then you will realize that the black and white TV converted into color TV, and then we are now having flat displays, and now we are talking about the foldable displays. But when we are talking about foldable displays and want to take it outside of the house and watch in the open environment, that means we are talking about the energy which is required to run these displays. That means you should have to have either battery or supercapacitor connected with this display. Now, battery has its own life, so you cannot run it for 24 hours because display size will be much bigger. And then the problem comes here that how long display can be run, because once you are out of your house, then you may stay there for a couple of hours. So taking up that display back to home and charging again will become a difficult task. So what should be done is you have to improve the display quality itself. That means we have to think about the display which can run with very low voltage or very low potential, and then it can run for a longer time. So that battery or supercapacitor which you are using with display can stay for a longer time with you. And that means it will serve the purpose. So that work has been done by nanometers, because with the black and white TV, which was bigger, and slowly it moved to your wall side, and now it is coming in your pocket. And if you look at the circuitry at the back end, then you will realize whatever wires are being used or cathode tube has been used has become very small. The circuitry has come into printed circuit boards, and then CRT has converted into liquid crystal displays. In that line, there is one concept which is in the market right now. It's field emission displays, where you require very small potential to run very colorful displays with very bright HD quality. But when you're talking about that, you should know really nanotechnology is going to help us in the future. Because if you look at the basic advancement in science and technology, it has happened every century twice, and the people have created massive wealth. In India, it has started with railroad, textile, and then automobile. So we are very strong at automobile. Even we are very good at service sector in the computer. So right now, what's happening is the development in the computer is reaching to its saturation. So end growth is happening. You might be saying that no, computer is still running. Obviously, computer is still running. We may move towards the atomization using the computer. But what I'm talking here is the development in actual development of computer. That means how the processing in a computer can go faster and faster. Right now, there are certain computers which is been claimed by China recently that they have developed a computer using quantum dots which can perform certain calculations very faster compared to all other computers across the globe. So that's what development is. What will happen next to that? That hardly we can increase the speed of the computer. Size of the computer may go down, but that has already decreased drastically. So what happens next is end of this computer development process. Now we will be running with processing or software development and all those things. Automobile already has reached to the saturation. Now this automobile and computer has been clubbed together. So you can see driverless car running on a road. Google has done that. Now what next coming is a nanotechnology. So far we are using nanotechnology only in the laboratories, and few things are coming in the market. So widespread adaptation, which is expected to be start very soon, maybe in a couple of years, maybe 5 or 10 years later. So this nanotechnology will be widely adopted in next few years, maybe 100 years. And after that, it may reach to the saturation. What is next after that? So as you can see, every technology has been connected one over the other and led the development of third technology. So automobile and computer has been connected together, then coming up with a diverse car. So what I believe that nanotechnology and computer will be coupled together, and then AI will be starting very soon. So artificial intelligence will be the next technology. So at present, we are running with the word nanotechnology. So we should understand why nanotechnology is so important. So when you're talking about nanotechnology, we have to reach to the base first, where exactly this nanotechnology is coming. And that is happening only because of the nanostructures. So far, very well known 4 type of structures are present, right? And when it comes to the nanotechnology, there are 3 more important nanotechnological terms. First one is 0D, then second 1D, and third is 2D. What happens here when people are synthesizing these materials, they prepare the particles which is having all three dimensions less than 100 nanometer. That means if you are talking about Cartesian coordinate system and XYZ axis, then all three dimensions are less than 100 nanometer. But what else we can do here is either we can go for decoration of these particles or formation of core cell structures or composite. That means we are talking here putting up one or two materials together to enhance the properties. So here, putting up two materials at nanoscale level is really a great advantage. So when you are putting particle over the particle, it will form a point contact. And when you put a particle in a core format or cell format, then it will form a surface contact. In next dimensional nanostructures, it will grow in one direction. So confinement will happen in other two directions. So here, normally decoration of 0D particles is to be considered. Being it in a one-dimensional format as like printed circuit boards, these are very good conductors because they can carry the electrons from one end to other end with very less resistance. But when you put them in contact with 0D particles, then they can form a very good point contact. If you are thinking about putting one material over the other, these 1D materials, nanomaterials are very good templates, so they can give you a core cell structures. Apart from that, you can put these particles inside one-dimensional structures. They can act as an impurity. Sometimes it's really necessary, or it can form a composite. If you increase other direction of this one-dimensional structure, then that will convert into a 2D format. So sheet-like structure is the best example of it. So you can have a composite of two different materials together. But forming core cell structure with these 2D nanostructures is very difficult task. But you can go with better ribbon kind of structures, wide angle, and then you can convert it into a better seed formation. So these 2D structures can easily be connected with 1D and 0D structures. Suppose you put it with 0D structures, then they can form a point contact. That's the reason these nanomaterials with 2D format are more attractive for supercapacitor applications. Even you can put it in contact with 1D structure, they will give you a perfect line contact. So that way, these 2D structures in stacking format are useful for a variety of energy applications. What left next is a 3D structure. Obviously, it looks like to be a bulk, but nowadays these are considered to be an hierarchical structure where you can have a combination of 0D, 1D, 2D independently. So you can have their interconnections and very porous nature. But when you look at the scientific development, the 3D structure, which are mimicking a little bit bulk morphology, were known to the scientific community. And because of thin films, 2D structures attracted more attention. And after that, because of quantum dots, 0D structures were explored more. But converting these all morphologies into 1D format was a difficult task. So that little bit lagging there. So let's have examples how these 0D, 1D, or 2D structures are more important. When you look at 0D structures, as I mentioned, they are confined in all three directions for the electron movement, because having dimensions less than 100 nanometers, then what are the applications they are? These 0D structures, which are also called as quantum dots, are very good emitters. So they can have single exciton emission properties. So these are being used for medical imaging, cancer imaging purpose. You can see these mice, and these different particles have been placed at different places. So they can be excited with different wavelength, and you can easily detect. So these are being used to diagnose the cancer cells. Not only that, these 0D particles are being used in optical storage. You might have heard about gold converting to red or different colors, because gold is golden in color, but when you reduce the sizes, they change their color because their photonics is changing. So like that way, different size of dimensions of these 0D particles can be synthesized, and you can use them for the optical storage. Apart from that, LEDs are being generated with the 0D particles with different colors. Earlier time, only red color LED was available in the market, but now you can see the 7 different colors with these LEDs. Dyes organic dyes are being also prepared in 0D format. Quantum computing, as I have given an example earlier. So this has been increased with the quantum dots. Importantly, these 0D particles are being used in a security purpose, because these 0D particles have single exciton properties. So they are being quoted on your certificates which having single exciton property, so that you can decide what kind of wavelength you want to be in your certificate, and then you can go for a security purpose. Quantum dot solar cells are also there. Dye-sensitized solar cells where quantum the 0D particles are being used, and also silicon single crystalline solar cells are also being there. But apart from that, these quantum dot solar cells or 0D particle solar cells are attracting more attention. So this is the best example over here. You can see the 0D particles decorated with 1D titanium nanotubes, and their dimensions varies from 2.3 to 3.7 nanometer, roughly 2 to 4 nanometer. And they form a rainbow kind of structure. And because of that, their efficiency has increased drastically, solar conversion efficiency. And based on that, it was being told in 2014 that these quantum dot solar cells can easily give efficiency close to 60% as high. That means actual power conversion efficiency will reach to 30%, which will be a groundbreaking for the solar cell applications. Later on, what left is 1D structures, which are a little bit difficult to synthesize because these can act as very good template. They have very good advantage of interconnecting in electronic circuits, large surface area, because they have very large aspect ratio and they can improve the applicability. But why they were lagging behind is because of their desirable qualities, because they always required to have identical shape throughout the synthesized film. Also, they required a uniform size distribution over the large area. Perfect crystalline structure is what is demanded for this one-dimensional structure. Stable chemical composition is also required when you are synthesizing thin films using these 1D structures and their individual dispersions. Because all these desirable qualities always act as in complexities. Getting the uniform morphology or uniform dimension in a single run on one particular 1 cross 1 centimeter square area is a difficult task. When you go on synthesizing these one-dimensional structures, either using chemical or physical processes, then chemical composition at center and at the outer area used to change drastically. So stoichiometric chemical composition is always a difficult task. When you reduce the size down to nanoscale, then their melting point decreases drastically, so stability becomes an issue, and they always found a self-assembling mechanism. So getting up individual dispersion is again a difficult task because the catalytic particles will decide how they are going to grow. So with these complexities, these structures were lagging behind. But around 2003, this Professor Shia from Georgia Tech Institute, he has introduced some growth strategies where these one-dimensional structures can be grown. First one was given to the solid anisotropic crystallographic growth, where the growth will happen in both the directions. Second one was a liquid-solid interface, where vapors will attach in a liquid format and convert into a solid, so that growth will happen in one particular direction. Or you can use one-dimensional template of one particular material, and second material can be grown over the other. Or you can go with size reduction. Probably the carbon nanotubes can be the best example, where winding up of two-dimensional structures converted into a 1D structure by size reduction. There's one more method where quantum dots or zero-D particles have been assembled in one particular line to convert into a one-dimensional structure, or going for organic methods where capping reagents can direct the growth in one-dimensional structure. So these other 5 methods will have less resistance, but when you are connecting these zero-D particles one over the other, being contact with next particles, their contact resistance will be very high. So these are the different morphological forms which are available in the literature. If you compare 0D structure and 1D structure, 0D structure typically when you say, then we will realize with the particles like which is circular in shape. And then based on 7 crystal systems or some morphological alterations, you can have certain limited morphologies. That is not the case in one-dimensional structure. Here, you can have a wide variety of structures. You can see here a root shoot structure, then one side or two side comb-like structure, different kind of hooks, belt, and then needles, also barcode kind of structures, helix where you can control actually defects inside the structure and tailor the electronic properties. Then you have zigzags. This also again controlling defect levels, bullets or brush kind of structures. So variety of morphologies are available with this 1D structures. And let's move to 2D structures, which is again attracting more attention nowadays. The graphene is the one of the best example to realize how these 2D structures are more important. Now, getting a graphene in a large area is not an easy task, even though you are synthesizing it using a chemical vapor deposition. But Samsung has recently introduced this graphene over 30-inch square area with uniform deposition. And these are being used as a flexible displays with very high transparency. Now, the question here is how much graphene they have put. Because when you are preparing a displays like this, then you require more material. Now, if you look at the liquid crystal displays and the size, then you will realize they are being used in bulk quantity. But when you are talking about displays in a flat panel, then we have to consider a very thin layer. So it is more important to understand how much graphene is required. So let's have an exercise and connect these all examples together, because we are talking here about one-dimensional structure and then 2D structures with 3D dimensions and all those. So when you want to put a paint on those bodies, then you will realize that the elephant size is much higher than you required certain kgs of the paint, which suppose considered to be a graphene, then it will go much higher. But people are thinking about converting Empire State Building, which was the first highest building of the world. Later on, many higher buildings come out, but this is the first highest building. So people are thinking about converting this whole building into a display by putting up graphene. So just imagine how much graphene is required. Right, let's have an exercise and understand first that number of carbon atoms per unit area. So you have to look for the periodicity. So if you look at this diagram and then put you in a periodic format, then you will realize that one graphene chain has 2 atoms putting together. So this is the periodicity of the graphene. That means we are considering one hexagon where you have 2 atoms in complete carbon atoms in one hexagon, and then you try to find out the area of hexagon first. So single hexagon area will go to 0.05 nanometers square. And here we are talking about Empire State Building, which is having height of 381 meter, length is 130 meter, and then width is approximately 57 meter. So if you calculate area of this particular building, then it is much higher. It's approximately 1.5 into 10 to 15 meters square. And here we are talking about the nanometer size. So putting up these carbon atoms in a single layer format on this building will be a difficult task. So that's why you have to understand how many carbon atoms you require, because when you are talking about the graphene, that means you are talking about single atomic layer of the graphene. So here, number of carbon atoms here will be close to 6 into 10 to 24. And then you will realize that considering these 6 protons or neutrons, that total weight will be at 12 gram. So we require just 120 gram to cover whole this building. So here is 2D materials coming in picture to change whole scenario of this display technology. Now, is graphene only the material in this race? Of course, no. If you consider graphene family, graphene is there, white graphene is there, black carbon nitrogen controlled, then fluorescence graphene, graphene oxide, these are there. But apart from that, they have the 2D chalcogenides and 2D metal oxides. Graphene family is more explored, and later on, this goes to 2D chalcogenides, but 2D metal oxides are not yet been explored yet. If you look at the properties of those particular materials, then you will realize this all 3 categories having a monolayer stable condition at ambient conditions. So whatever blue color is here, these materials are considered to be very much stable at ambient condition, even though they are existing in a monolayer format. But when you go to this middle portion, where mostly 2G chalcogenides and 2D oxides are present, so they are considered to be stable in air, but yet more detailed literature needs to be explored. After that, these 2D metal oxides, particularly, these are actually 3D compounds in a 2D format. They are exploited down to a monolayer, but very much little information is available, because most of the time these 2D oxides either exist in a hierarchical structure or 0D or 1D format. So this is a very good chance if you want to explore these metal oxides in a 2D format. And these chalcogenides, which are there, metallic dichalcogenides and layered semiconductors of gallium, selenium or indium based materials, they are unstable in air, but they are stable in inert atmosphere. So these whole families of 2D materials are going to change the world in the next. But here we are focusing on MOS2, which is having a wide spectrum. Why these 2-dimensional materials are getting more attraction? Because if you look at this wide spectrum, from ultraviolet to radio waves, then all these 2D materials have been covered. Graphene is running in this race because that is covering visible to radio waves. It's a wide spectrum. But here we are focusing only on visible spectrum, where these metal oxides are being placed. So this metal oxide is having band gap between 1 to 2, YMO selenide is having a band gap between 1 to 2.5 electron volt. Now, what is more important when you are thinking about the 0D, 1D and 2D materials, and I'm saying here these 2D materials are going to run the race, then I would like to give an example, real life example, which is also called as a future minute mile. It was a thought for many years that running a 1 mile in 4 minutes is difficult task. It was also considered that no man can run this 1 mile distance in 4 minutes. But in 1954, the Roger Binster from Oxford University just took 1 second less, and he made a history by running this 1 mile distance in 3.59 minutes. Right. After that, after 2 months later, John Van Dyck from Australia took 1 second less. So these two guys made a history around 1954. But if you look at the present scenario, now there is no more history, right? Or there is no more thought that human body will not run such a distance in 4 minutes, because Usain Bolt, Van de Ven, these, if you ask them to run this distance, then they probably take 2 to 3 minutes to run this distance. So whatever thought was there, that has been turned out. And same thing might have happened with this graphene oxide or carbon nanotubes. For many years, it was thought that thermodynamically putting up single atomic layer is impossible. That means existence was not accepted. Existence of single atomic layer was not accepted thermodynamically. So Professor Ijima, when he introduced carbon nanotubes, what was happening here, these carbon nanotubes were folding up the single atomic layers. So when you look at the carbon nanotubes, then you will realize they were either 2-layer, 3-layer, or multi-layer structure. If it would have been opened up, then this would have been called as a graphene, what we are having right now, right? So thermodynamical thoughts not let it happen. That's what I believe. And then you know that Andre and Constantine from University of Manchester, they put a single layer of graphene by using just caustic. And this paper was submitted to the Nature initially with 3 pages, and it was rejected with 2 simple comments. One was saying that isolating stable phase with 2-dimensional material is impossible because thermodynamics says so. And prior to that, the carbon nanotubes were introduced with multiple foldings. And then second comment was it is not sufficient scientific advancement. You just can think about these 2 comments. Obviously, the method they used was very cost effective, and that's the reason it was correlated with thermodynamics as well. And because of these 2 reasons, this paper was rejected. And later on, in October 2004, this paper was accepted by Science, and the title of the paper nowhere says it's a graphene. It says electric field effect in atomically thin carbon film. They were talking about the single atomic layer. And after that, in 2010, both received Nobel Prize, and from that time onwards, 2D material became hot topic. What if you put these 2D materials with 0D or 1D? Then I believe they are going to be hottest, because here you are talking about combining 2 to get out this energy storage or display applications. So here we will see synthesis of some 0D, 2D materials together, 0D, 1D materials together, and then we will look through how they are being characterized, and then certain applications of these materials. So let's start with 2D, 1D nanoheteroarchitecture. So here, before I introduce with 2D, 1D nanoheteroarchitecture, I would like to know what was thought for before we start this research. If you look at this particular portion, titanium dioxide, which is easy to grow in a 1-dimensional format, and then MOS2, which is easy to grow 2-dimensional format. What was done here by Fu, this paper is published in Dalton Transaction in 2015. What they did, they prepared these 2 morphologies independently, and then they coated together. So this 2D morphology, when they try to coat with TiO2, then TiO2 particles will form on the surface of this MOS2, and rather than converting into 1D format, they convert it into a particle format. So this is like 2D and 0D particle structures together. Later on, they put another strategy where 0D particles, these 1D structures were being coated with 2D structures. What was the thought? That these 2D seeds will go deep inside the 1D format, and they will have a layer by layer structure within the 1D format. So this was actually imagination, but in reality, it happens to be different, because these 2D seeds, rather than going deep inside these 1D structures, they just load it on the top surface, and it become like a core cell structure. But core was a porous nature, and cell was completely covered. So what we were thought for them was not came in reality. And because of that, you can see here, when they control the 2D morphology, then this decoration was become difficult task. And you can see here, these 2D structures, when try to coat with the titanium dioxide nanorods, they convert into 1D structure. And that laid down to lower field emission properties. So here, the field required to emit the current, the density close to 10 microampere per centimeter square was much higher. And that's the reason this idea was failed down. And we thought, let's take this as a challenge. So initial task was to convert or to grow these 1D structures on the silicon substrate. Because getting up 1D structures, that too in brookite, is not easy task. Because when you look theoretical explanations, then you will realize that the particle size, if remains, or the structure size, if remains between 0 to or 1 to 11 nanometer, then you will have anatase phase. And once you move above 30 nanometer, then it will convert into a rutile phase. So you should have to have a size between 11 to 30 nanometer. Then there is a possibility of getting brookite structure. So here, when we synthesize, then top view, you can see this looks like to be a particle on the surface, but these are actually vertically grown one-dimensional structures giving thin film of approximately 600 nanometer. And these dimensions of these rods is less than 30 nanometer. It's between 5 to 20 nanometer. Now, here, the maximum rod dimensions were close to 10 to 11 nanometer. Now here, you can say that this probably anatase phase. But the X-ray diffraction and TM analysis shows the brookite phase. Now, question here is why we have observed this brookite phase. When anatase phase is synthesized, then to getting anatase phase, even though dimension less than 11 nanometer is required, the hydroxyl group is playing a major role. Suppose during synthesis your hydroxyl group exists, then definitely you will get an anatase phase. So we have avoided here the existence of anatase phase, and then we prepared this at very high temperature. It's close to 1300 degrees Celsius. And that's the reason anatase phase has not formed. Later on, these 1D structures have been decorated with 2D structures. We can see here these nicely grown 1D nanorods are there, TiO2 nanorods. And on the top, we have decorated these nanorods using 4 nanometer, 20 nanometer, and 40 nanometer thick layer. So when 4 nanometer layer is there, as I mentioned earlier, that nanorods can act as a very good template. So because of that, these 2D structures are nicely decorated, maintaining the one-dimensional morphology. When you increase the thickness to 40 nanometer, then being a top portion accessible to this 2D structure, they grow like a particle. So they try to maintain this one-dimensional morphology. And when we exceed this 20 nanometer thickness of this MOS2 to 40, then uniform layer decoration of this 2D MOS2 has been formed. So when you check the cross-sectional view, then you will realize that for 40 nanometer, all the gaps were filled and the thick layer was formed. After that, the question here was, when you are putting MOS2 on the TiO2, MOS2 itself not required an oxygen, because when it comes in contact with oxygen, rather than forming MOS2, at the interface it may form MO oxide, which we don't want actually. So we try to understand what happened at the interface. So TM was not giving us an information because these two phases were prepared independently in 2 different systems. So when you try to scratch out the sample and check with the TM, then both were independent. So finding out the interface was a difficult task. So what we thought, why not to use XPS, which is having a very good property. Actually, it considered to be a disadvantage because XPS gives you information on the range of 10 to 20 nanometer area. But we thought, let's take this as an advantage. Because when you are scanning up these samples in XPS, then only 10 nanometer area is accessible. So when we are increasing thickness from 40 to 20, 4 to 20, 20 to 40, then definitely this total accessible area for XPS is 10 nanometer is going to tailor hold the properties. So independent TiO2, when we scan with XPS, then we realize it remains to be 1:2 ratio approximately. When we are on 4 nanometer area, then TiO2 signal was exposed because in 4 nanometer out of 10, 6 nanometer was TiO2 and 4 nanometer was MOS2. So out of this 10 nanometer, TiO2 exists in larger quantity. So you can see here, TiO2 signal is still exists. When we move on 20 nanometer, then definitely TiO2 is suppressed because upper layer in 10 nanometer is MOS2. So we couldn't get signal from this TI and oxygen. Now, if suppose interface is having oxygen, then what we believe that interface oxygen will grow with the MOS2 and it may happens to be in 20 nanometer layer. So oxygen signal has not been observed. So what we believe that at interface, MO oxide has not formed. Now, if you look at the signals relatively to MO, and sulfur, then you will realize that when we are on 4 nanometer layer, the MO signal and sulfur signal is down because its layer was just 4 nanometer. But when we move on 40 and 20 nanometer, then obviously 10 nanometer was scanned, so you can see the signal remains almost constant. And then the further thorough analysis gives an information that MOS2 and TiO2 remains in their own nature rather than forming impurity phases at the interface. So when we convert this TiO2 into one-dimensional format, then turn-on field was quite higher, is more than 4 or close to 4 volt per micrometer. That too distance was varied, and the separation between the emitter and collector was close to 2000 micrometer. So when we put MOS2 independently, then this turn-on field was much higher, and it was approximately close to TiO2. Now, challenge here was when we putting up these two, this turn-on field should decrease drastically. So when we put up this on together, then what we realized that 4 nanometer layer of this MOS2 is reducing this turn-on field quite drastically. And when you go for orthodoxy text using theoretical values, then it apparently passed. That means whatever theoretically is being predicted is coming in actual experimental portion. And this device remains quite stable. Now, what would have happened here? That TiO2 is rich in electron, MOS2 is also rich in electron, but being in 4 nanometer layer, this TiO2 should have backed up this MOS2 and suddenly burst up at very low turn-on voltage into a large current. So once we realize that 2D and 1D structure are giving up very good field emission properties, which is having a field emission display probability, then we realize that this 2D structure, if it is in 1D format, that means it is having a point contact, then only it is emitting a better current. But when it is converting into a 2D format, then these whole properties are decreasing. So here we come with an idea, rather than putting 2D structures, just put 1D structure on the top of 2D structure. But here, 1D structure should be very stable. So this 0D structure is more important in this case. So what we did here, that first we grown one-dimensional structures, and then we decorated it with 0D particles. So this 2D structure has been eliminated out. Now here, rather than going one particular direction, here, to decorate these 0D particles, we decided to grow hierarchical structures. And for that purpose, we use the zinc oxide. So you can see the nice forest is been observed, and this having a tapered morphology. And these tapered morphologies are been decorated with 0D particles of the gold, because gold is having luminescence properties. And then this gold content has been varied, and then you can see here with 0D pure zinc, there is no gold, and then when you decorate with this gold, you can find a gold signal. And you can even see here, these gold particles are nicely decorated over this 1D structure. And the particle size is close to 20 nanometer. The max of the particles are having range between 18 to 21 nanometer. Now, what is being processed here? That gold concentration has been varied to decorate on this structure from layer by layer. So for this purpose, we have used different these reaction times. So you can see here, initially zinc remains intact in its own stable format. And when you decorate gold, as gold layer on the zinc oxide is increasing, so zinc signal is going down, and obviously the gold signal is coming up in XPS. And then you can realize here, when you increase the reaction time, the decoration of gold has reached to the saturation approximately in 24 hours reaction. That means after that, even if you put this zinc oxide rods in a gold solution, then no more gold is going to decorate on this particular structure. And then gold, rather than getting oxidized, remains in its metallic form. And then we study its field emission properties. So zinc in its initial stage was being in a tapered morphology, giving turn-on field close to 1.31, which was far better than earlier case as well with titanium dioxide. And we decorate the gold particles on the top of it, then this turn-on field has decreased drastically, reached close to 0.96 volt per micrometer, so which is much larger, right? Much better. So here what would have happened, this gold itself is rich in electron source, and when you put zinc oxide on the back of it, then this whole backup was bursting at very low turn-on field. So that is also been correlated with turn on voltage and then the 5 values. And then theoretically, you can see here, this is passing the theoretical test as well. So now, what about 2D structure? Because earlier I have said that 2D materials are going to run the list, because here we have correlated 2D, 1D, 0D, and 1D structure. So to have replacement for the graphene, new materials is coming up. But why graphene is so important? This is the first important question. Because what was thought? With these 2D materials, you can go for stacking one over the other, different 2D materials with different properties so that you can have a better material. So that means we are talking about here, putting one over the other. And so selectivity become here an issue. Or selective removal of the one up to the other phases become an issue. So to mimic this, there is one more family coming up in the market is Maxine, where this layer by layer structure is possible. So here you can see this Maxine derived from MaxPhase is having 2 different layers, titanium and carbon layer, and in between this aluminum layer is being removed out. And this has been done through the MaxPhase. And this has been discovered by Yuri Gogusty in 2011. So in preparation of Maxine, MaxPhase is more important, where aluminum do exist, and these are 3 families so far been explored for this Maxine, where this M and T is more important. T is, stands for functional group, M is here with these different elements, A probably aluminum is mostly used or silicon, but there are other metals that have been also explored. And carbon and nitrogen is unreplaceable, either carbon or nitrogen you can use, and these are the different functional groups that have been used. And this Maxine is having wide variety of applications, including environmental, optoelectronics, sensor, biomedical application, energy storage, and many more. So this material is going to run the future. Now, what is most important thing here, how this Maxines are being synthesized. Either it is being used in microwave-assisted molten salt or plasma sintering, where 90% or 99% purity can be observed. But if you look at these both techniques, they require very high vacuum. So the cost of the MaxPhase preparation goes higher. In India right now, it is available with 10 gram cost approximately 25 to 30,000. So challenge was reducing down its size, the cost. So here what we did, rather than going for high vacuum techniques like pulse resolution or spark plasma sintering or solid-state reaction, we have modified this process and we come up with an idea of molten salt synthesis which can operate at ambient atmosphere rather than using high vacuum. And you can see here, these different concentrations have been mixed together in aluminum crucible and reacted at 1350 degrees Celsius, and then nice Maxines are being observed over here. And then you can see the surface area has quite increased. So at one particular temperature, which is called 90 degree with different reaction parameters, then 99% pure MaxPhase is observed. So you can see here, the MaxPhase at different reaction parameters been forming a layer by layer structure. And when you etch out aluminum from this, then slicing has been done and the separate layers are being observed. So this has very good energy storage mechanism as well. So once Maxine has been formed, you can see the surface area has drastically increased as like graphene. And then you can see here this XRD shows that perfect crystalline morphology. Now what is most important, this particular material is showing very good applications for lithium-ion batteries, sodium-ion batteries, supercapacitor. Apart from that, it has been shown very good hydrogen storage and production properties as well. So like this way, with these 2D and 1D structures connection together or 2D, 0D structures connecting together, you can either go for energy storage or catalysis, because these Maxines are also being used for photocatalytic water splitting applications. So these are our collaborators who has helped us for this research work, and these are my student who has done all this work. And last, I thanks to the funding agencies for supporting my student and my lab. And thank you for the organizers for giving me chance to interact with you. Thank you.
Thank you, sir. Thank you for such a nice presentation. Sir, shall I ask one question? There's a question from participant.
Yeah, sure.
Yeah. The question is how the electrical property of OD material varies and controlled when quantum dot size decreases from 10 millimeter and below, nanometer and below.
10 nanometer or below.
Yeah.
See, theoretically, quantum dots do exist, but particularly I won't believe on the quantum dots because once you convert these quantum dots into actual size, then they falls into a nanometer size, right? So accessible electrons on the surface changes, and that's the reason their electrical property changes. That means we are really talking about the atoms at down to the nanoscale.
Okay. Okay, I think that resolves the query of the participant. Thank you so much, sir. Thank you so much for your wonderful presentation and covering the topic that is nanomaterial engineering for optical and energy applications. It was wonderful listening you, sir.
Yes.
Before we move on to the formal vote of thanks, there are a few instructions for the participants. As we have got almost more than 75 abstracts, and the abstracts have been selected for paper presentation, the paper presentation session is divided into 4 groups, and 4 different links have been provided in the WhatsApp group and Telegram group. So according to the groups given, the participants are supposed to join the link, that is Google Meet link, which is provided on the specific groups. So after the formal vote of thanks, we will have a half an hour break, and after the half an hour break, you can connect on those Google Meet link. As well, if you have any queries, you can ask on the WhatsApp group. So before we conclude this session, I hope the participants had a very enlightening session. And now I request Mr. Sanjay Gaikwad, Head of Physics Department and Organizing Secretary of the International Conference, to propose a formal vote of thanks.
Thank you, madam. It gives me immense pleasure to give a vote of thanks of today's program. I extend my heartfelt gratitude to all who made the International E-Conference on Advancement in Material Science, Trends and Application resounding success. Very thanks to overwhelming response from every corner of India and outside the India. Total 5 countries participants are involved in this conference, and from 25 states participants are registered for this conference. I am also special thanks to our esteemed keynote speaker, Professor Deepak Dubal sir, for sharing valuable insight thoughts on the low carbon emission technology for the manufacturing of the suitable materials, new aspects in batteries, and also on the new aspects in the batteries. Thank you for giving valuable insight on this topic. I also, our distinguished invited speaker, thanks for the Dr. Rahul Salunkhe for the giving talk on MOF derived nanoporous for energy storage application. And the third person, Professor Suresh Devan sir, on the topic of designing the nano hetero architecture for the future energy application. I am also thanks for the enlightening these talks on the nanomaterials. And also thanks to our session chairs, will be held oral presentation by the Archana Patil Kalekar madam, Dr. Abhijit Kadam, Dr. Bhavesh Sinha and Dr. Deepak Gaikwad. I am also thanks to our principal, best principal, Dr. Ganesh Thakur Sahib, who motivate us to organize such a program. I also thanks to the NB Power sir and RMS Vice Principal for their unwavering support. I would like to express my sincere appreciation to the IQAC coordinator, Mr. S.L. Govind, for ensuring the quality of this event, as well as all head of the departments, teaching staff, including our genius faculty, Dr. Geshgun sir, and other Mr. Ajay Dodi sir, Ravindra Molbekar sir, Ms. Benjir Mirza madam, and non-teaching staff for their dedication and hard work. I also thank our esteemed research scholar, Sushant Prasad, Prathamesh Katare, Prathamesh Udekar, Gauri Patil madam, Mahesh Sarkar, and all students for your active engagement and enriched our discussion and contributed to the success of the conference. I also extend my thanks to all participants and presentators who make this event grand success. A big shout to the talented anchor, Dr. Leena Mishra madam, Mr. S.L. Goyal sir, Dr. Nitin Sasane sir, Miss N.N. Gaikwad madam, whose helped completed session with fineness. Together, you have all played a vital role in making this conference and platform for knowledge exchange and collaboration in the field of material science. Thank you once again for your commitment and enthusiasm. Let's look forward to more such enriching endeavors in the future. Very soon, we share the 4 groups separate Google Meet link. Have a patience. Thank you.
Thank you so much for joining. And I'll conclude this link here. We will meet again on the separate links which will be provided on the groups. Thank you.